بسم الله الرحمن الرحيم والصلاة والسلام على سيدنا محمد عليه أفضل الصلاة وأتم التسليم. Good morning everybody. It's my pleasure to start our day with the panel discussion. Please Dr. Abu Zahra, the chairperson, the moderator for the session. The panel discussion will start now. Please, the speakers come to the floor. Thank you very much.
Good morning, everyone, and welcome to the second day of the symposium. So we'll start with the session. Okay, sorry. So our panel session today, where we start this day with, will tackle the topics of carbon capture and hydrogen economy. What are the obstacles for decarbonization, technologies expansion? We'll touch a bit on the hydrogen production. We'll talk more about opportunities for carbon market, business models, and so on. So we have three speakers or panelists with us today. The format will be each speaker will be given 5 to 10 minutes as an introductory remark in terms of presentation or a brief introductory. Then we'll go through some sets of question and discussion, and hopefully, if the time allows, we'll keep 5 to 10 minutes to engage the audience and get some questions and input from you guys as well. So our first speaker is Mr. Kazunori Koiko, who is the Deputy Manager at JGC Corporation. He has 20 years experience in process engineering, specialized in petroleum refining, LNG, natural gas processing, and is currently leading a blue hydrogen project since 2021. Mr. Koiko, the floor is yours. Thank
you. Assalamu alaikum. Good morning. Let me at first focus on my presentation theme of integrating the carbon capture with hydrogen production. First of all, I will show the status of the carbon capture in using the three graphs. At first, let's see the trend of the carbon capture in the past. The left side graph shows global CCS capacity trend classified by each plant phase from 2010 and to 23, which is actually exactly same as the graph used by Mr. Abu Zahra yesterday. And it includes not only the operational CCS capacity in dark blue, but also the project in construction, advanced development, and also early development phase. The horizontal axis is in million tons of CO2 captured, sequestered per year, and rapid increase is shown, but the operational CCS capacity is still slightly less than 50 million tons per year. And they are located in the North and South America, Middle East, China and Australia, Europe and China and Australia. More and more projects in the development phase implies a big surge in the future. Then the graph in the center is a backcasted CCS capacity by emission source announced by IEA in 2021 in their net zero by 2050 report. This is not a forecast in line with each country's policy or pledge. So it actually well exceeds the city policy or announced pledge scenario. The vertical axis is the gigatons of CO2 and the capacity, if we look at the capacity in 2020, that is less than 0.05 gigatons of CO2. so corresponding to the left side graph in dark blue. According to this milestone, in 2013, for example, several hundreds CCS facilities are expected to start their operation by 2030, and several thousand of facilities by 2050. IEA actually updated the graph last year, incorporating the latest information as shown in the right graph. And the milestone of CCS in 2013 decreased to 1.0 gigatons CO2 per year, but it still needs several hundred CCS facilities by 2030. oapec countries are showing strong presence in this reference, occupying 8% operational performance in last year. And oapec countries are considered in very favorite condition for CCS because for the three reasons. First one is they have the intense CO2 emission point source cluster, and then they own the expertise of the hydrocarbon industry, which can be directly applied to the carbon capture, transport, and storage. And then they have the abundant storage capacity and geological data. In the right graph, we can see the hydrogen in dark blue. So we can see the significant role is foreseen for the hydrogen production because it's in the net zero emission scenario in the right side of the graph. It occupies around 150 to 200 million tons of CO2, which corresponds to around 20 million tons of hydrogen production. Considering the total hydrogen production capacity worldwide is slightly less than 100 million tons last year, so additional 20 million tons is very significant. So let's see how to integrate the carbon capture with hydrogen production. This is the typical block flow diagram of hydrogen production using the hydrocarbon feed. The requirement of the oxygen and the steam depends on the process of the hydrogen production. And in this industry, three processes are available: steam reformer, ATR, and POX. And which process is suitable depends on the plant condition, such as the CO2 capture rate or hydrogen capacity. When integrating the carbon capture, for the location of the carbon capture, three options are available at A, B, or C. A is on the synthetic gas line, having the highest pressure and CO2 partial pressure, so it is the most favorite condition. And B is on the PSA tail gas line, if PSA is applied for the hydrogen purification. Both A and B can capture most of the carbon contained in the hydrocarbon feed. In the case of steam reformer, SMR, heating as a reformer furnace is required for the endothermic reforming reaction. Typically, this additional heating emits 40 to 45% of the carbon dioxide from SMR. So if CO2 capture rate of, for example, 90% is required, carbon capture needs to be installed at C. On the other hand, ATR, if we use ATR, ATR supplies the heat needed for the endothermic reaction by its oxidation and partial oxidation process. So the additional heating is only required for the preheating of the hydrocarbon feed before being fed to the HL burner. Therefore, higher than 90% of carbon dioxide can be captured either at A or B. In terms of the hydrogen production capacity, SMR steam reformer is said to be reasonable at smaller capacity because the economy of the scale doesn't work for the SMR. So ATR becomes advantageous when the hydrogen production capacity increases. The break-even point...
2 minutes.
2 minutes?
2 minutes.
2 minutes, okay. The break-even point of capex between SMR and ATRs is typically 100 to 200 kilonova cubic meter per hour. As for the technology of choice for the carbon capture, chemical absorption is expected to play a major role in, at least in the short term, considering the maturity of the technology. High-packed is one of the chemical absorption process jointly developed by JGC and BASF, the chemical company in Germany, with the target of CCS. And high-packed has two references. One has started up in 2012 for a natural gas processing plant, and the other is under construction for the blue hydrogen now. It can strip the CO2 at high pressure, 3 to 5 bar absolute at stripper, because high-packed solvent has higher thermal stability. High-packed has also higher absorption performance of CO2, so combining these advantages, high-packed can offer to support the installation of carbon capture in, of course, in the OPEC countries by reducing the both capex and OPEX. Thanks for your attention.
Thank you. Thank you, Mr. Cook. So our next speaker is Ms. Mikoko Senshi, is the Research Director in Energy and Sustainability Division at Mitsubishi Research Institute, and comes with more than 15 years experience in carbon credit generation. So floor is yours. You have like 10 minutes for introduction. Thank you.
Thank you very much for your kind introduction, and good morning, ladies and gentlemen. And I'm very honored to have the opportunity to speak here today. And I want to thank both organizers, the OPEC and JCCP, for giving me this opportunity. So next page, please. Oh, okay. So, okay. Okay, so let me start with introducing my company first. So many of you have probably heard Mitsubishi named companies, but you probably have not heard of Mitsubishi Research Institute. We were established in 1970 at the occasion of the 100th anniversary of the Mitsubishi companies. But we often get asked this question, but Mitsubishi Research Institute is not part of Mitsubishi Corporation. We're not part of Mitsubishi Heavy Industries. We're not part of Mitsubishi Electric. We were founded by our brother and sister Mitsubishi companies, but we are now independently listed in Tokyo Stock Exchange with our own unique shareholder structure. And we are especially famous in Japan for having #1 market share in the Japanese government research and consulting market. We now have more than 900 professionals serving in advisory and consulting in wide-ranging fields. And as my topic of presentation, the carbon credits, is concerned, we have in-depth expertise, especially in terms of developing the CO2 accounting methodologies and also advising the government of Japan for designing the rules and guidelines for the joint crediting mechanism, which I will explain a bit more in detail later. We are also expanding internationally. We opened a regional office in Dubai in 2021 for the Middle Eastern region. And since then, we are building partnerships with institutions around the region. And as far as the Saudi Arabia is concerned, we had an opportunity for our chairman, Mr. Morisaki, to meet His Royal Highness Prince of the Saudi Arabia last year alongside Japanese Prime Minister, Mr. Kishida, when he visited the country last year. And we also had the opportunity to sign MOUs with CAXT and CERC in the Kingdom of Saudi Arabia. We are also very active in engaging in climate change-related discussions with a variety of stakeholders in the region. For example, at COP28 last year, we participated in side events alongside the Qatari government, Al-Attiyah Foundation, and Islamic Development Bank, and so on. And as for myself, I have close to 20 years of experience working on carbon credit generation through both the multilateral and bilateral scheme. And for the past few years, my focus has been very much on the CCUS. We have worked on developing CCS guidelines under the JCM for the Japanese government. And we are also engaged in global policy development and research and consulting for CCUS and hydrogen. And I have studied the role of carbon credits in incentivizing both CCUS and hydrogen. Okay, let me move on to introducing you to how the carbon market is at the moment. The landscape of carbon market is quite complex. On the demand side, we have country governments with national emission reduction targets that may want to use carbon credit as one of the methods for meeting the targets. And we also have private sector companies that have the voluntary targets. And we also have some sector-specific activities, such as the aviation sector under CORSIA, that are required to meet certain emission reduction targets. And as part of that, they also require carbon credits. And on the supply side can be roughly categorized into three different aspects. One is the international agreement-based carbon credit mechanism. So in the past, it was Kyoto Protocol and CDM, and now it's the Paris Agreement, Article 6. And another supply source of carbon credit is the country and regional programs. More and more governments now have established the domestic crediting schemes, both to meet the national emission reduction targets, but also to help the companies located inside their countries to meet their voluntary targets. For example, Japan has the J credit scheme for their domestic market. And thirdly, we have the voluntary carbon credits. Many of you may have heard VCS, the Verified Carbon Standard, or Gold Standard. They're quite famous around the world for producing the voluntary carbon credits. And this landscape is getting even more complex lately because some of the public schemes allow the use of voluntary credits, while corporates are using not just the voluntary credits, but all sorts of credits for their voluntary use. And lastly, I would like to mention that as the carbon credits are used to offset the remaining emissions, basically they first make the efforts to reduce emissions, then they will use the carbon credits to offset the remaining emissions. So eventually, they will need to be replaced by the carbon removal for achieving their net zero targets. Now let's look at the carbon market trends in terms of the credit issuance. It was steadily on rise in the late 2010s, but has slightly stalled in 2022. And this is due to the challenging macroeconomic conditions globally and uncertainties and integrity of the carbon credits. And if you look at the breakdown of the type of carbon credits that are being traded, the portion in gray in this graph, which is the voluntary carbon credits, they are the largest proportion of the carbon credits in the market at the moment. But you can see that the orange portion in its graph, which is the government or country programs, and they are steadily gaining prominence. I would like to also bring your attention to the bilateral schemes or the Article 6.2 programs under the Paris Agreement. And a number of countries participating in the bilateral mechanisms are increasing. And they are most of the time initiated by the buyer countries or the countries that want to procure carbon credits, such as Japan, Singapore, and Switzerland, and so on. And the Middle Eastern countries are positioned uniquely in this landscape, I would say, because, for example, the Kingdom of Saudi Arabia have signed on to the joint credit mechanism in Japan since 2015, and UAE just signed the JCM agreement last year. And under the JCM, they're basically the supplier countries of the credits. But you can see at the bottom of this chart that countries like UAE and Kuwait also are engaging in their own bilateral negotiations as potential buyer countries. And their partners in this case will be some African countries. So I think Middle Eastern countries are quite uniquely positioned in terms of the bilateral schemes. And I would like to touch upon a little bit in detail about the joint credit mechanism. This has been a Japan-initiated mechanism since 2011. Japan started this initiative as an alternative to CDM originally, and now they're engaged in this mechanism as a pilot Article 6.2 program, and they have 29 partner countries so far. And the way it works is that the Japanese government provides funding to help facilitate technology transfer and project development, as well as capacity development to enable Article 6 transactions. And in return of that, Japan will have access to emission reductions, which takes place in a partner country. And this JCM has met some success so far. We have more than 200 projects at the moment among the 29 countries. Okay, so this will be my last section. So there are challenges and opportunities in carbon market, and there are certain things that need careful consideration before when you think about how to make use of carbon credits to benefit your activities. First of all, as I explained earlier, there are many different types of carbon credits, and you may wonder what types of credits are good credits, or what types of credits should I use. I think first you need to clarify the objectives of your of using carbon credits. If you are a country government that want to use carbon credits to meet the national reduction targets under the NDC, the first obvious choice would be through Article 6, either Article 6.2 or 6.4 under the Paris Agreement.
If you may conclude in a minute or so.
Thank you. But if you are a private company with voluntary reduction targets, you may want to use voluntary credits. And if you are a technology developer or a project developer using advanced, expensive technologies, for example, you may want to attract finance and use credits to attract finance. And this may be possible through bilateral credits, such as JCM, or voluntary credits that can sell your credits at a high price. Second aspect that you need to consider is the integrity. You may have read some newspaper articles criticizing carbon credits for the past few years, and how to avoid it, or how to make sure that your credits will be high standard. There are some international standards that are in place, and you might want to make sure that the credits you want to create or you want to purchase meet these standards. And last but not least, plan ahead of the opportunity. As I mentioned before, carbon credits can be a useful tool to attract investment or to attract finance, and to facilitate activities to meet certain policy or national agenda. So I think if you plan well ahead, I think it's highly possible that carbon credits will help facilitate the realization of your objectives. And you can use carbon credits to test technology or test the mechanism for MRV or the registry. And whether you may end up using Article 6 or not, I think there's a very big room for taking advantage of the capacity development programs that are provided through Article 6, for example, through the World Bank, through Japanese government, through other country governments, or through other independent organizations. They offer capacity development programs for Article 6 or carbon credit generation. So there's definitely room for making use of that. So thank you very much. That's the end of my presentation.
So our third speaker for this session is Dr. Nasser Aouda, a lead researcher from CAPSARC, working on CDR, bioenergy, carbon capture and utilization. He holds more than 20 years experience in the field in both academia and consultancy with bachelor and PhD in chemical engineering, energy, and environment. So Dr. Nasser, the floor is yours for your introductory remark.
Thank you very much, Dr. Mohammed, and thanks to my colleague. My colleagues already have given a good intro to the technology and the market, so I don't have slides. So I'm just going to be given a very brief few minutes on really the perspective in terms of hydrogen economy. So I'm not here talking about the challenges for deploying carbon capture on hydrogen plants, not the challenges for the market, but rather the challenges for the hydrogen economy itself. And you know, we all know that hydrogen is needed. It's part of the decarbonization. It's one of the solutions. In addition to what we mentioned yesterday, CCUS, renewables, energy efficiency, and you know, obviously offsetting and direct air capture and carbon dioxide removals and so on. Hydrogen, really, as a carrier, it's not new to us. I mean, it was before. There was an economy based on hydrogen, but then we replaced it with natural gas for reasons we all know. And when we talk about CCUS, the low-hanging fruit, basically, in terms of capturing the CO2, is hydrogen plants, ammonia plants, in addition to natural gas processing and so on. So that's easy to capture the CO2, so it's understood. However, what I would like to highlight in the next few minutes is the challenges in terms of adopting a hydrogen economy. This is clear from what I have seen throughout the many years in the UK, for example, in terms of what we're trying to do. I mean, just first to highlight that actually a hydrogen infrastructure, or moving to hydrogen, is a new thing. If you look relatively in terms of the decarbonization journey, we've been talking about renewables for the past 20, 25 years. Hydrogen only came about in the past 10 years. You know, initially the CCS discussion was around coal and gas, then it moved to industry, then CO2 utilization, and then BECCS, and removing CO2 from, for example, from biomass combustion, and then recently also actually capturing CO2 from hydrogen plants, existing hydrogen plants. So it's really a relatively new thing. But the challenges being faced currently in the West, for example, and in the UK, is if you need to adapt hydrogen infrastructure, you need to change the pipeline. Many of the UK pipeline, for example, the transmission pipeline is steel-based, right? So basically, corrosion is a major issue. So that needs to be changed. This is a major cost. This is not, for example, the problem in Ireland, because Ireland, obviously, they have a newer pipeline, which you don't need to adapt. You can just use the existing natural gas pipeline. So this is really one of the key issues is being considered. The other thing is you need to look at the end use of hydrogen. If we are combusting hydrogen in smaller engines, in boilers, there are some still safety issues need to be resolved. For example, in the UK, I can mention that actually they're talking about 20% blending of hydrogen with natural gas, and take that process gradually rather than combusting 100% hydrogen. There are still some safety simulations and modeling which needs to be undertaken to understand what would happen if you combust 100% hydrogen in engines. Major cogeneration companies like CHP companies, combined heat and power, for example, like Yimbacker, for example, they already mentioned to you, for example, for smaller engines, less than 1 megawatt electric, they are able to combust 100% hydrogen, for example. But for larger, above 1 megawatt, this is still to be resolved. And they think, from recent discussions I had with them a few years back, by 2030, they will be able to develop engines which will be able to combust 100% hydrogen. So these issues still need to be considered. I mean, yes, hydrogen infrastructure is a great thing. It's part of the solution. But there are some aspects in terms of the transport infrastructure, as I mentioned, in terms of the end use, which also need to be considered. And the one last thing I would like to highlight is, I mean, obviously, this idea of hydrogen being part of basically developing the hydrogen infrastructure is taken seriously, for example, in Europe. Why? Because recently, Europe, for example, until recently, there is something called cogeneration reference values, where you compare a combined heat and power against a power-only and a heat-only reference value. And at the moment, until recently, there was no consideration of hydrogen as a power-only solution. But now in Europe, there is an efficiency developed for hydrogen, both on the heat side and the power generation side. We still don't have a lot of experience in terms of combusting pure hydrogen. Again, it's being considered. The last thing I would like to highlight is we talk about blue hydrogen versus green hydrogen, and there are so many colors of hydrogen. But unusually, I mean, there was a recent study 2 years ago which talked about basically that blue hydrogen will perform very badly in comparison to green hydrogen in terms of life cycle emissions. This study was based on the US. And the reason why it showed that blue hydrogen is performing bad because of the methane leakage from upstream processes in the US, very, very high leakage. And so that showed when you compare it to life cycle, I said, you know, electrolysis processes are performing much better. However, we do not have this issue in Saudi Arabia, for example, because methane leakage is minimal. Methane emissions are controlled very well. So if you do the analysis for Saudi Arabia, it will show actually blue hydrogen will perform very well in comparison to green hydrogen from a life cycle point of view. So I just wanted to highlight these issues, the infrastructure issues, and you know, hydrogen economy, yes, it's part of the solution, it's a great thing, but there are a lot of challenges still at the higher level to be overcome. Thank you so much.
Thank you, Dr. Nasser, and thank you for our panelists for the introductory remarks and presentations. When we talk about CCS, we talk about hydrogen, we talk about the integration, we always touch on the obstacles related to the technology development, economics, and then policies. I want to start the discussion touching on these. So if I can start with you, Mr. Kazunori, on the technology, especially on the carbon capture technology, how can that help making hydrogen production more cost-effective and environmental friendly and more sustainable?
Yep, sure. To answer to that question, I have prepared one presentation slide. Can you show my slide, please? Which is the which explains our technology impact more in detail. As I explained in my previous presentation, I said the high stability and high absorption performance can reduce the cost of the carbon capture for the hydrogen production. And that slide explained how that higher thermal stability and performance, higher absorption performance influence the cost of the carbon capture. Okay. So I will start my my explanation. The high impact is basically same process as the conventional amine solvent-based chemical absorption. So the circulating amine solvent will absorb carbon dioxide and strip it at CO2 stripper. And the conventional amine solvent typically strip the CO2 acid gas at the regenerator at around 2 bar absolute due to the temperature constraint at the regenerator stripper, which is around 120 degrees C or maximum 130 degrees Celsius. However, HYPACT has the higher thermal stability, so it can resist against the higher temperature, let's say 150 degrees Celsius. And that corresponds to the operating pressure of 3 to 5 bar absolute at the CO2 stripper. And this difference between 2 bar absolute and 5 bar absolute is, thanks, number 5 sheet, 5th sheet. Next, yeah, that's one. Yeah. The difference of the CO2 stripper pressure has a significant impact on the performance of the CO2 compression because the HYPACT can reduce the compression ratio significantly. Assuming the storage pressure of 200 bar, if we use a conventional amine solvent, the compression ratio will be 100, which is the 200 divided by 2. But if you use the HYPACT, the compression ratio can be reduced to 40. And if we use the centrifugal type CO2 compressor, we can eliminate the first stage of the compressor. So that can reduce the plant cost significantly and also energy demand because the compression ratio can be reduced significantly. That is how higher thermal stability influence on the cost reduction of the carbon capture process. And then, yes. Then, how the absorption performance will affect the cost of the carbon capture. Higher absorption performance will enable the HYPACT to operate at the less solvent circulation rate, and the equipment size, the size of the equipment piping in the carbon capture plant is basically proportional to the solvent circulation rate. So reducing the less solvent circulation rate can reduce the cost size of the equipment and piping, and so reduce the plant cost. And also, the energy demand is also proportional to the solvent circulation rate. Therefore, especially the reboiler duty, so the opex can also be decreased. So, this is one of the solutions, how the HYPACT can make the plant cost effective for the CO2 compression and carbon capture. Yeah, that's.
I think we need to see these advanced technologies, and we also say, like in some parts of the CCS and hydrogen, people see like compression or dehydration being mature, so not much could be done, but a better integration, a better improvement could help reduce the cost. The other element in the discussion is the policy, Ms. Senshi, and when we talk about international and government policies, will they accept a certain color of hydrogen, for example, for import, export, offtake, incentives that being deployed in the different countries that will support or prevent the deployment of CCS and hydrogen? How do you see that in terms of policies and incentives at local level and international level?
Thank you for your question. I think policies have a big role in the promotion of the so-called low-carbon hydrogen. And I think the trend now is that there is no color differentiation in terms of what hydrogen can be accepted. I think different countries have set carbon intensity standards for the low-carbon hydrogen. It differs whether it's the EU or the US or Japan. But as far as the Japanese government is concerned, their policy is that they will not differentiate between the colors, but they will accept hydrogen as long as it meets the certain standard for the carbon intensity. And I think it's important to understand how to calculate the carbon intensity. And this is being discussed. The methods of calculating carbon intensity is being discussed internationally in an organization called IPHE. And the Japanese government, for example, is following the activities in IPHE to develop their own guideline for the carbon intensity calculation. So I think it's important for the exporting countries to understand that trend in the methodologies for calculating the carbon intensity, and to also work towards the harmonization of such methods. I think that it's already moving towards harmonization, but I think it's important to make sure that you're engaged in the discussion. So, you will not be needing to calculate depending on which country you export to. So that's one policy trend on a global scale. I think if you look at the local scale, many countries are adopting policies to financially support either hydrogen production or the CCS implementation. And for example, the Japanese government are in the process of implementing the policy to support the cost differentials for the conventional hydrogen and the conventional fuel and the low carbon hydrogen. And that's, again, their plan is not to differentiate based on the color of hydrogen, but the carbon intensity, as well as what cost can be incorporated into the calculation of like the bidding price, for example. I think that needs a careful assessment. And again, it's a very much ongoing discussions on the policy development. So I think it's important to keep track of the policy development. And I think this may not be addressed directly from your question, but I think in terms of the CCS, I think it's important that the countries make sure that there is a policy to ensure the transfer of liability, because that's considered one of the high risks for implementing CCS in various countries. So the countries that implement CCS, they're expected to have a framework in place where it's clearly defined, how long the operators need to monitor and at what point the operators can transfer the responsibility to the government. It might not be a big issue in the Middle East, for example, if the government is the operator of the project. But again, I think it may depend on each project, and I think it needs to be clearly defined when and how the transfer of liability takes place. And whether the CCS is conducted independently or if it's conducted as part of hydrogen production, I think that the liability issue will still exist. Thank you.
Thank you. And I think talking about low carbon hydrogen and not looking at the production method or the color, at least at our institute, this is how we see things should be moving forward. How to calculate carbon intensity is very essential. Then each production method will be affected by the production technologies deployed. And that brings me to you, Dr. Nasser, on when we talk about what's called the blue hydrogen, CCS integrated with the natural gas processing, and then how that can influence the cost from the economics point of view, because it's like some people claim that other technologies has more clearer economic approach or calculations for the cost. If it's a green hydrogen or turquoise hydrogen or whatsoever, it's more clearer and kind of like fixed and designed type of chain. with blue hydrogen, we have the obstacles of CCS. I don't know if it's an obstacle from economic point of view or not, and that's the question. Because there are liabilities, there are changes in the future that might result in additional cost, or maybe that's a potential to reduce the cost of CCS, and therefore hydrogen production cost will go down. So how do you see carbon capture impacting the economics of hydrogen production in comparison to other hydrogen production technologies or routes?
Okay, thanks for the question. I mean, obviously, when integrating, carbon capture, utilization, and storage with SMR processes, steam methane reforming, obviously, this will impact the costs significantly, let's say. So the way, by the way, obviously, it's applying CCS could be applied not just to, for example, SMR. It can also be applied to gasification of biomass, for example. If we have gasification of biomass to produce hydrogen, which is still a technology which is not mature enough. It's not like as mature as SMR. But let's say we're talking about SMR now, just focusing on SMR. This will be additional capital investment, additional capital cost. And it's not just the CO2 capture itself. It is also the transport and storage infrastructure, which also needs to be taken into account. So when we talk about blue hydrogen, we're talking about this additional TNS infrastructure. It's a complex and expensive infrastructure. Who's going to develop that? Who's going to be responsible for it? Luckily, this is something which needs to be shared amongst not just the hydrogen sector, but also amongst the power sector, the cement, iron and steel, the refineries, so many other sectors which need to chip in terms of developing this infrastructure. What is the best way of developing that? Currently in Saudi Arabia, for example, there is work going on to try to develop a RAB model, similar to what has been developed in the UK, a revenue asset-based model, where somebody can invest in the TNS infrastructure and then perhaps take payments for CO2 being taken into that. So yes, the cost will involve all these things. Also, the adding CCUS to existing hydrogen plants will also impact the operational cost, because you have amines, or let's say amine was the solution. It has new solvents, adsorbents, whatever you're going to be using, maintenance costs for the capture plant, many other things which obviously need to be taken care of, additional fuel requirements to run the capture plant. So this will also impact costs. But obviously, if carbon emissions are taxed, then in the long term there will be cost savings. So really, what we need is this incentive. We need the incentive to do that. So CAPSARC recently did a study on actually the cost of blue hydrogen. And for gray hydrogen, the cost came out, for Saudi Arabia specifically, came out to be $0.9 to $1.2 per kilogram of hydrogen. So this is that range depending on the price of natural gas assumed. And 40% of that cost is the CAPEX cost, with the OPEX being 15%, and the remaining, which is 45%, is basically the fuel cost, natural gas. The CAPEX in this case for gray hydrogen, if you want to build a gray hydrogen plant from scratch, it's about $900 per kilowatt of hydrogen produced. But if you are going to add CCS to that, then the cost, based on our calculations, CAPSARC calculation, increased to 1.65, from 0.9 to 1.2 to $1.65 per kilogram of hydrogen. And 50% of that now is a CAPEX cost. Right? So basically, which is around, the CAPEX cost in this case is around $1,700 per kilowatt of hydrogen capacity. So as you can see, that actually this is like a 40% increase when you add CCUS to gray, what we call a gray or SMR plants. But luckily, where, for example, in this region, or specifically in Saudi Arabia, where the benefit is that actually the TNS cost, the transport and storage cost, are small in comparison to other countries, because many of the sources, many of the hydrogen plants are actually placed on top of the reservoirs, first of all, and the transport. These are very large sites with transport costs are minimal. So there is a big advantage, actually. This is why hydrogen is seen in Saudi Arabia as a low-hanging fruit in terms of CCS deployment. okay? And the additional benefit will be the production of hydrogen. So really, one thing I can also add is basically a good strategy is to consider blue hydrogen and green hydrogen, and not to focus, as some countries have done, they just focused on green hydrogen as the solution and abandoning blue hydrogen altogether. It needs to be, a mix of the two. I mean, blue hydrogen should be seen as an interim to an era where actually green hydrogen becomes much cheaper. At the moment, it's very expensive. Thanks.
Thank you, Dr. Nasser. I want to pause and involve the audience. If there are questions, please come to the microphone, state your name, and if it's for a certain speaker, please address it to that speaker.
طيب, السلام عليكم. Good morning. My name is Hamza Al-Nizam, and I have two questions. The first question is, what is the basis of carbon pricing? The second question is related to, there was a lot of wave and rhythm for all these green projects, all these, and people were focusing on low-hanging fruits. And now we started to see a wave of a lot of companies, international companies or countries, start to postponing their plans. So initially some companies, they put 2030 plans to achieve carbon neutral. Now it is being dragged 2050, 2060, and so on. And the reason, in my opinion, is that we finished the low-hanging fruits. There is no clear agreement on the path forward. And many of the technologies that came, that didn't prove yet to be economical. So how do you see the path forward? Is this wave going to slow down? Or there will be some more logic into what we are trying to achieve, really? And I think many of your guests here can answer this question. Thank you.
Thank you. So we can start maybe with the carbon pricing and the basis for that.
Yes, I think carbon pricing is introduced, the way it's introduced differs from country to country, and the two common ways of carbon pricing are emissions trading scheme and the carbon tax. An emission trading scheme, the most historical and famous one is the EU ETS. And in the EU, you probably are aware already, but each facility that emits the CO2 is prescribed a certain level of emissions or benchmark. And if your emissions go above that, you need to purchase the emission allowance from other facilities. But if your emissions go below the benchmark, then you can sell the difference. And that's how the pricing works. Pricing basically works on market, the supply and demand. And carbon tax is introduced in some countries, and that's basically a government decides, the tax rate for a ton of CO2. And I think this is related to the pathway towards the technology development or deployment. But the carbon pricing is very important to ensure that the technology is deployed for long term. I think in the short term, maybe the government incentives and financial support may work for the initial technology deployment, but for the long term, for that to continue, I think the carbon pricing is very important, because the entities that either adopt or deploy technologies, they need to see the financial merit. If they're in the technology. So I think I might pass on to other speakers to maybe comment more on the
second question.
Yeah, the second part of the questions. Yeah.
Yeah, sure.
Yeah.
I can comment on the second question. I haven't personally been following the cancellations in terms of green or blue hydrogen plans, but I've been following the CCS, for example. But the same principle here applies. What we're talking about here are technologies which obviously need incentives, need financial support, and unless you have that support, projects will not be feasible. So you need that support. There are commitments and priorities. In the UK, for example, we had clusters of Merseyside, Teesside, and so on, where basically the government now recently just changed their mind, although initially they said, we want to support blue hydrogen and green hydrogen and all of that took, and then suddenly there was some kind of so there's a delay in these projects. It's because the incentive is not available. The other thing you need obviously, one thing we have to worry about also the planning and the permitting for projects. I mean, in some countries it's more pronounced than others. So really, there is no doubt we need these technologies, green hydrogen, CCS, blue hydrogen, but we need the policy. We need the incentives to be able to support projects. And if that doesn't happen quicker than the technical development of it, then yes, cancellations will continue. I've seen over the past 20 years, I've been involved in CCS, I've seen so many cancellations of CCS projects. In Europe, in the US, it's either because the technology is so complex, it cannot be done, but mostly, and if you trace this back, it is mainly due to the fact that the incentive, the policy is not available. And we are basically now, we are at a point, and we were talking about this yesterday, we are at a point where 2030 is our target. If you want to achieve the targets we have in terms of CCS, hydrogen, DAC, anything, you need to start now, because it takes time. There's a lead times here, 3 or 4 years to develop projects, even more in some cases. If you don't start now, then we can already say now, maybe next year or the year after, that we are already late. So it needs to start now, immediately.
Yeah, thank you. I think we have 5 minutes left in our session. So I want just to give the concluding remark for each speaker, a minute or two. So if I can start with you, Mr. Kazanori, closing remark, commenting on, for example, the collaboration between Japan and GCC countries, ammonia, blue hydrogen export, import.
Okay, thanks. As a conclusion remarks, let me introduce one good example of collaboration of this area. That is blue in the field of the blue ammonia. Before introducing the example, let's see how the ammonia will be used for in the future, in the sustainable future. Ammonia will be expected to be applied to the one is power generation, electricity generation, and also the shipping of fuel. And according to the IEA's net zero scenario, the blue ammonia is expected to play a significant role and for the blending of the fuel for the electricity. 100% of the blending is expected a milestone in 2050. And also for the shipping, ammonia, blue ammonia is also expected, so it is also the promising technology. And as a collaboration example, for example, from the Saudi Arabia to Japan, on the 2020, they achieved first demonstration of the blue ammonia, and just last year, they delivered the first cargo of the blue ammonia to Japan, which is used for the power generation in a Japanese petroleum refinery plant. And also, just last month, the United Arab Emirates also achieved the first delivery of the certified low carbon ammonia to Japan. So such an collaboration between the OPEC countries and other countries like Japan will be more and more important for our sustainable future.
Thank you. That's Ms. Sinchi, on final remarks.
Yes. Thank you. As I mentioned during my presentation, Saudi Arabia and Japan have already signed agreements on the joint crediting mechanism back in 2015. And there are 3 registered projects between the 2 countries at the moment. But there has been there's been a bit of a slowdown in terms of the project development in the JCM project development in Saudi Arabia. And I think this might be a good opportunity to revisit the bilateral agreement that we have in place and consider, what type of projects that are worth collaborating on, and perhaps we can consider hydrogen, or perhaps we can consider carbon removal. Carbon credits can work for testing new technologies. So maybe it's time for us to consider, new target areas for joint investment.
Thank you. Dr. Nasser, we're supposed to talk about business models, but I think the time is limited, so maybe in a minute, what you could conclude or some final remarks.
I mean, yes, I mean, collaboration, knowledge sharing is really very important for us to progress, definitely. I mean, I think linking the different aspects of, because these technologies and these systems will be competing with each other eventually. Do we use renewables to decarbonize the electricity grid? Do we use renewables to produce green hydrogen, or do we use it for DAC? There will be competition. So really looking at integrated system, integration, where we can basically improve efficiencies. I mean, in terms of the oil and gas industry and downstream, which is the main title of this event, is basically looking at and we'll have later another session looking at the different decarbonization methods. But obviously, energy efficiency is the low-hanging fruit. We look first, renewables, carbon capture, but hydrogen also has an important role to play. And I think my recommendation out of this really is to be that all solutions should be considered at the table, should be put at the table. Green hydrogen and blue hydrogen are both a solution, but definitely many countries are leaving blue hydrogen behind. It shouldn't be left behind.
Thank you. So I would like, please join me in thanking our speakers for their contribution in this session. We tried to be exactly on time, so I hope that's good. Lots to talk about. It is the time simply to make an action and move forward with more projects, business model, incentive, built on collaboration and policies. Thank you all for your contribution, and thank you for listening.
I would like to thank Dr. Abu Zahra and all the speakers for these fruitful discussions. Now we will have a short break, and we will back by 10 quarter, inshallah. Thank you very much. This is sorry for that. We will try to. Welcome back to the fifth session. I would like to invite the chairperson for the stage and the speakers. The session entitled is Initiatives and Efforts to Reduce the Carbon Emissions. Please, the floor is yours.
Hello, how are you? Shall we get started? I'm Kazuki Yamamura. Today's this session 5's chairperson. So this session 5 title is Initiatives and Efforts to Reduce Carbon Emissions. It is a basic and very important topics. So let's get started. The first speaker is Engineer Salem Al-Dahami from SABIC. With a bachelor's degree and over 30 years of experience in chemical engineering from King Saud University. He has been responsible for SABIC's global processes technical support since 2013, leading innovative improvement projects. He has authored several technical best practices and is currently focusing on decarbonization project. Please get started.
Assalamu alaikum. Good afternoon, good morning, sorry. It's my pleasure to be here with you to present this topic. I'm going to talk about hydrogen as a clean fuel to steam cracking. I'll be talking about the downstream, the end use of the energy transition. So the end use of the hydrogen, how the hydrogen, after making available, be used in particularly an existing asset was not built for it from beginning. So we're looking at technical challenges in most of this paper, and just let's go. So talk about introduction. I'll talk about what's first adopter, hydrogen combustion and steam cracking. I'll talk about technical challenges, and then I'll end up with conclusion. So decarbonization, so SABIC is being at the end use of the energy resources, decarbonize hydrogen, blue hydrogen or green, the energy, the electricity, the green electricity, and also the carbon capture as resources to decarbonize the existing asset. SABIC is a major petrochemical producer, and for decarbonization, we're looking at these main three energy transition resources to be able to decarbonize our asset and operation. So the first adopter at chemical commercial scale for steam crackers, the objective of the project is provide technology at commercial scale for steam cracking furnaces And why steam cracking furnaces? Because the steam cracking furnace is a piece of equipment that consumes a lot of energy, a lot of energy. So talking about SABIC, it consumes about 20% of the energy. SABIC is, the emission is in the neighborhood of 45 to 48 million ton of CO2 per year. So 20% of that is very significant. Number two, the steam cracking furnace is a piece of equipment that is pushed to the edge of, to the limit of the material, of the science, of the technology. So, therefore, the furnace, I think many of you are aware, has to work in semi-batch system. So, because it reaches the end, the limit of the material, of the technology, of the catalyst, and then it has to go out for regeneration, be able to take another batch. So it's, therefore, as of today, there is no existing proven technology of hydrogen combustion, electrically heated furnace, and my colleagues will talk about the e-furnace and the demonstration that we have done, and also the CO2, the direct CO2 capture from flue gas. So there isn't commercial proven scale of these technologies, and SABIC First Adopter is a project to prove these technologies for widely used in case of these resources, the green energy, the green electricity, the blue or green hydrogen, and the CO2 capture resources and hubs are becoming available in the near future. So we know how to just connect to these resources and start our decarbonization journey. So we have time. Okay, so all these three adopter projects are to start, and actually they have started. We are in the study phase, and we are to start the operation of these projects by 2027, 28, collect enough design, operational reliability information so we can possess the know-how to apply these technologies to an existing asset. So let's focus more on the hydrogen combustion. I will leave the rest to my colleagues. So hydrogen combustion is different than methane, of course. It leaves behind no CO2. That's great. Yeah. However, there are different challenges. The hydrogen per unit energy has larger volume. So to adapt to an existing asset has not built for it from beginning. We have to consider that in terms of modifying the burners, modifying the system, the piping, the valves, the hydraulics of the system, and so on, to be able to adapt hydrogen combustion. Hydrogen differs from methane, quite significantly, and we can see hydrogen firing requires less oxygen and air for the same amount of heat. So you can see the heat, the amount of oxygen is almost half. Hydrogen firing requires less fuel for the same amount of heat. So there's less amount of hydrogen to be consumed to deliver the same amount of energy. Flame speed is one of the challenges, and significant challenges. So flame speed for hydrogen is much higher than the flame speed of methane, and that has to take into a very important consideration in the design of the burners. Adiabatic flame temperature of hydrogen is significantly also higher than methane. As you can see, 2400, almost 2500 degrees C versus 2200. And putting this in equipment that's already pushed to the limit really makes it nearly impractical. So we want to explore all these technical challenges in our hydrogen combustion first adopter. So in the first adopter, we want to demonstrate hydrogen combustion in one furnace. We want to change the design. We want to review all the aspects in terms of reliability, of course, reliability, and before that, safety in the plant, just to make sure that we can do this not only for the furnace, but can be done in a wide application of the furnaces. So impact on the burners in a furnace. So the impact, the higher flame speed and higher adiabatic flame temperature cause actual flame temperature to increase. And that could push the NOx generation beyond the permissible limits. Also, higher tube metal temperature, whereas, as mentioned, is pushed to the limit. It can also shorten the furnace run length and make the cycle of the furnaces more frequent, increase the radiant box efficiency, and then reduce the amount of flue gas and make the steam generation of the furnace is less. So we have to compensate that by maybe another fired equipment, auxiliary boiler, and so on. The higher flame speed requires higher fuel ejection velocities for pre-mixed burners. So there are different types. So there are different types of burners. Raw gas burner, pre-mixed burner, and the pre-mixed burner is really challenging application because, as mentioned, the hydrogen speed is very high, and it causes flashback, and that's a safety and reliability issue. So we have to encounter that in the design of the burner. For high hydrogen content, diffusional flame burners could be required. However, burner manufacturers are recently developing new designs for hydrogen service. And actually, throughout our project, we discovered that all the burner OEMs are actually set on a race to demonstrate and develop hydrogen-capable burners. So impact on the furnace overall, so the lower volumetric flow through the radiant box and convection section. So higher heat in the radiant section, we will fuel basically combust less fuel in the radiant section, and we will generate less flue gas. And as mentioned before, the hydrogen require less oxygen, and then less air, less flue gas, and then generate less steam and the recovery and convection section. So we have to supplement that steam by maybe another auxiliary boiler. So that's another thing. Also, the NOx generation, already the existing burners and furnaces are operating at the maximum permissible level of NOx emission, and the hydrogen combustion is operating at higher temperatures. So that's another challenge. So how we are going to mitigate the NOx, the new level of NOx by the hydrogen combustion. The higher firebox temperature causes an increase in the radiant box efficiency, and we talked about that. Changes in the hydraulic loads and on the fuel gas, as mentioned, the volume of the hydrogen is larger. We have to do retrofit, considering everything from the hydrogen source all the way to the burner, including the burner itself. Just to illustrate, so if we have to completely eliminate CO2 by converting the fuel to hydrogen, we have to go all the way to 100% hydrogen, and that's very challenging. These are two reference points of what is the composition of the fuel in a naphtha cracker versus ethane cracker. So the ethane cracker typically would have something like 75 mole% of hydrogen in the fuel. We generate less CO2, but as mentioned, if you want to completely eliminate CO2, you have to go all the way to 100% hydrogen combustion. The NOx formation, so that's another thing. So as we all know, the thermal NOx increase with the temperature. Current burners are limited with this regard, and we are working with different OEMs, seeing what's in there. There are tricks applied to comply with the NOx limitation. So part of it is basically staging fuels. So combusting part of the fuel in an oxygen lean environment, and then the rest of it in oxygen rich environment, get the lower temperature in the combustion, get lower NOx. So there are ways to do that, but considering other limitations and considering the practicality of operating the steam cracker, whatever burner we have to adapt has to be fuel flexible. So for example, in a startup situation, we have to, the burner has to be capable of combusting almost nearly 100% methane. So it has to be a fuel flexible design. So, the NOx issue is not only a single burner emission, it takes into consideration, the entire furnace. So, as you might know, the flue gas flow within the firebox is laminar, and there's higher residence time. So there could be, and there is, additional NOx generation while the flue gas moves around in the firebox in a laminar scheme. So that's quite challenging. So we can adapt a burner that demonstrate compliance with NOx limits, but when we put multiple burners in an actual furnace, the result might be quite different. So in conclusion, so SABIC first adopter hydrogen combustion team is exploring best available burner technology and furnace licenses. So because time is of essence, we don't want to develop this ourselves. We want to collaborate and get a technology from whoever can demonstrate it the quickest. Such technologies are emerging without prior proven commercial scale. So everyone comes and claims that, yes, he has a hydrogen burner and a hydrogen flexible burner, but that's only a single burner. No one has demonstrated that yet in a commercial furnace. Further, plant will require fuel flexible burner, as mentioned, to satisfy plant operating scenarios like startups and so on. The first adopter is to prove in commercial scale, and that's what myself and my team are working on. There is industry challenge, which is large quantities of hydrogen are required with lower footprint of CO2 than combustion natural gas. So that's, with this, I conclude my presentation. Thank you.
Thank you for presentation. We have about 4 minutes, so does anyone have any questions? Please.
As you know, the combustion reaction divided 3 types: lean mixture, rich mixture, and stoichiometric. The best for 3, the stoichiometric. In the case of lean mixture, give excess of oxygen. And with rich mixture, this is a big problem, give CO2 and CO. My question about type of flame, stationary or moving flame, this first question. And the second question, how can control on the flame speed and if we used H2 instead methane, and how can control on the flame front temperature? Thank you so much.
Thank you very much for the question. I would start with the second part. The flame speed has to be controlled by the design. So there has to be enough velocity, jetting velocity to the tip of the burner to get the speed higher than the hydrogen flame speed. Because if it is equal or less, then the fire will travel backward and cause fire within the burner, and if that allowed to be persist, will pose a safety issue. So within the design of the burner, the jet speed has to be higher than the hydrogen for all kind of operating scenarios: the startups, the normal operation, the turn down, etc., etc. I think the first question was about the CO. I'm sorry. Can you repeat the first question?
As you know, the flame, two types of flames, stationary and moving.
Right. So.
For example, for combustion engine moving, happens with the boiler and stationary.
Right. So in our steam cracking furnace is stationary. Yeah. Yeah. Thank you.
Thank you. Any other? Okay. Thank you very much again. So next presentation is the speaker is Mr. Nasser Aldaran from SABIC. He joined SABIC in 2014 as a scientist, focusing on hydrogen production from water using solar energy. He holds patents and now serves as senior manager, resources, and infrastructure. He has worked on projects like COTC with Aramco, plastic waste treatment, and synthetic gas conversion. He holds a master's in process and polymers engineering and a bachelor's in chemical engineering with honors. Please get started.
Assalamu alaikum, and good morning, everybody. Thank you for being here, and I'm happy to be here among you to present to you one of the initiatives that we have in SABIC in the decarbonization field. My presentation will be continuing the presentation Salim have started with, which is an e-furnace first adopter project. Just a background, and you might have seen the summary in my colleagues Uthman yesterday, so I'll go over it very quickly. SABIC is committed to the Paris Agreement, where we target to be carbon neutral by 2050. As an intermediate target that we are seeking to reduce our scope 1 and 2 of GHG emissions by 20% by 2030, comparing to our baseline of 2018. And we have also started to work with our partners in also reporting our scope 3 emission. So in order to reach carbon neutrality, there are 5 main pillars that we believe that it will play a strong role in achieving this carbon neutrality. The first one is reliability and energy efficiency improvement. Okay. Where we believe that increasing the efficiency of our existing assets, as well as designing our future assets in a very efficient way, will play a really major role in reducing our GHG emissions. The second pillar is the renewable energy that we plan, or we aim to have 50% of our consumption of electricity coming from renewable by 2030. This can be done through signing PPAs to buy the renewable energy, as well as to buy the renewable energy certificates. We know that there are many projects in the renewable energy field, and we are aligning our target to the country's target of reaching 50% of our consumption from renewable energy. The third pillar is electrification, which my presentation today is about, that we plan to develop and also acquire technologies that will be able to convert our fossil-based assets to electrical ones, which eventually will have to be run by renewable energy to reduce the carbon emission. Fourth pillar is the carbon capture, that we also plan to capture the CO2 produced in these assets. And the last one is the green and the blue hydrogen. This can be considered whether it's an energy carrier, or it can also be used to produce low carbon products such as green methanol, green ammonia, or low carbon methanol. So the decarbonization principle, that the carbon neutrality technology roadmap of our technology and innovation structure to develop and validate toolkit of technology options. So until 2030, that we plan to continue our efforts in improving these technologies in commercial scales. And we believe that the next large CO2 reduction will come from three main key decarbonization principles. The first one is the hydrogen combustion, which my colleague Salim presented. The second one is electrification, that I will present today. And the third one is the carbon capture, which my colleague Amar will present shortly. So it's really important to highlight that we are planning to prove all these technologies together, because we believe that there is no a single option in achieving our decarbonization target. So each site will have its own utilities, its own resources, and its own regulations. So we believe that our aim is to prove these technologies in parallel, and in the future, deciding which technology will be deployed in which site will really depend on these factors. So we are moving ahead with proving these technologies in commercial scale, and we are recommending to prove these technologies in order to really be implemented in our existing assets of steam cracker furnaces, as well as to gain the experience in engineering and operating these new technologies. So we have been advised to proceed and work with our affiliates on site in determining which technology will be fitting their own decarbonization roadmap. So just an overview of the opportunity, that the execution of the first adapter is, as mentioned, is crucial really for the decarbonization target. And the first technology is the hydrogen combustion, which my colleague Sana presented, where the key principle is to replace the methane by hydrogen. The second principle is electrification, where we plan to replace the fired burners by electrical heating, which obviously will be run by renewable energy, in order to consider it as decarbonization technology. Third one is the carbon capture, where we plan to capture the CO2 produced in the steam crackers. So just to give you an idea, that we have started demonstrating our demo unit of e-furnace. So this is the technology which is co-developed by SABIC, Linde, and BASF. So back in 2002, we have signed a GDA to develop this technology, and by late May, beginning of June, we have actually commissioned the first demo unit of electrical crackers which is almost have the capacity of almost 2 tons per hour. This project has been granted support by the German government of 14.7 million euros, which really helped us to build and start operating the unit. So the aim is to use these learnings from the demo unit and apply it to the first adapter commercial scale unit, where we plan to scale the capacity by a factor of 15x comparing to the demo unit. The commercialization of the first adapter that we are targeting to have it late 2027 to the beginning of 2028, where we plan to actually to build and start operating an existing e-furnace parallel to our existing crackers. Location of the furnace itself has not been decided. We are currently evaluating different sites and options, whether it could be in our KSA assets or in our abroad assets. As well as we are also trying to decide also if this would be used in gas or liquid feedstock type. So the principle is that we have two different heating mechanism where we plan to operate the furnace at 850 degrees Celsius by using electricity. This can be done either by direct heating, where we plan to introduce the naphtha to the cracker. The second one is the indirect heating, which is a toaster type of configuration, where the coils will be heating the furnace to 850 degrees in order to crack it. This technology, if renewable energy is used, will be able to reduce CO2 equivalent emission by almost 90%. There is still some steam will have to be imported to the system, as we are not using methane, that we will be having less flue gas to export. So this is why the emission will be reduced by 90% and not 100%. So this is just a configuration of the principle is that we are planning to introduce the new electrical furnace at commercial scale to be placed among the existing gas or liquid furnaces. So this would be a new built commercial scale furnace. This furnace will be able to, depending on the flexibility that you have on the downstream, this could be an additional furnace. If there is no availability or capacity in the downstream, we will be able to either shut down one of the existing furnaces for maintenance or have it as a standby furnace in case it needs to be used. So principle is the same. We will have the same product. We believe that the mass balance will be similar, the quality of the product will be similar. But using such a furnace with the renewable energy, of course, will be able to have a low carbon olefins that could be eventually be used in chemical or polymers industry. The driver of our project is cash flow driven project. As we do have a very close target of 2030 to reduce our CO2 equivalent gases. So this is just a timeline that we plan, the timeline that we anticipate for this project. Currently, we are at gate 2 of SABIC gating system, where we will be able by Q3 to start hopefully the engineering and feed for this unit. And hopefully that FID will be late 2025, and we plan to have the startup late 2027 to the beginning of 28. What would be enable us for this project? The key is renewable energy, the availability of renewable energy, as well as the affordability of renewable energy. The second one is that it could be the case for any decarbonization initiative where economics could be challenging. This is why premiums on the product are really necessary for us at this stage. The third pillars will be the subsidies, governmental subsidies, which will really help us to have an attractive business case that will allow us actually to implement this at commercial scale. This is it from my side, and thank you very much for listening.
Thank you very much for your presentation. We have about 7 minutes, so does anyone have any questions? Please.
Thanks for your very interesting presentation on the service strategy for the decarbonization. As you introduced the three technologies, one is the hydrogen combustion and electrification and carbon capture. I understood that if one of the three is applied to your cracker, the other two are not required. So, for example, if the hydrogen combustion is applied, the heat is already enough, and electrification is not required, and also the flue gas does not contain the carbon capture, so carbon dioxide, so carbon capture is not required. So I understand that one of the three will be selected as a result of any comparison or evaluation. So the question is, if all the three technologies are proved to be technically feasible, how to compare and evaluate and decide one of the three technologies? Thanks.
Thank you very much for this question. Yes, so as I mentioned, that we plan to prove all these technologies spontaneously. And the decision is that if all these technologies have been successful in deployment, the choice for using which technologies to be used on which site will really depends on the many aspects, the availability, the utility availability, as well as the feedstock availability, as well as the regulations. I will give you an example that in our East Coast, for example, that we believe that hydrogen would be available in commercial scales. And it might not be the case in the West Coast, where actually more renewable energy projects will be introduced. So which sites, which technology will be used, depending on really which availability of utility will be used, as well as what would the regulation allow you to do so. In our European assets, for example, that we know that there could be a future restriction on actually hydrogen firing. So this is why that it might not fit that specific location. So geographically, challenges as well as regulations will really play a big role on that. CCS, for example, that we know that it is just limited to the well availability of. So CCS might only apply to places where there is actually availability to store CO2. So this is why that the choice eventually depends on really which utilities and sources are available to that region, as well as the regulations of that country. Thank you.
Any other question? Okay, please. Yep.
Thank you so much for presentation. As you know, the source of CO2 is combustion of hydrocarbon and coal and gas. This refer or sense the problem of product countries. This, I think so, this problem globally,
Yeah.
for all world. My question about the final product, you talk and we talk about the CO2 capturing. CO2 capturing, if we capturing a huge amount, milliard ton, bigger than of CO2, where we used, I think used in EOR, enhanced oil recovery, this is take little amount of CO2. If you have any method for use this CO2. Thank you so much.
So just not to spoil the next presentation, my colleague Omar will have a dedicated presentation to CCS. So hopefully more insights will be given during that presentation.
Thank you. So, okay, please.
Thank you very much. I understand the SABIC strategy very well. Could you just tell me there is Aramco
Yeah.
and you are SABIC. There are many common issues of
True.
interest. How do you cooperate? How do you share the research technology with Aramco and SABIC? That's one of the basic questions, including CCS or those hydrogen.
Yes. So this could be actually an overall question regarding decision making as well as strategies between the two companies. But as you are aware that currently SABIC is 70% owned by Aramco. So there are always really regular talks and discussion really regarding strategy, not just in decarbonization, by the way. I think there is always a discussion regarding strategies in overall industry of the petrochemical. So I'm pretty sure that there is a very good alignment in the decarbonization strategies of the both companies.
Maybe especially like CCS, you may need some place to bring. So some issues are very closely connected between your research and activity of Aramco. Is that true? Or
Yeah. I mean, at the end, Aramco is the operator of the wells and they're actually the one who are really leading the CCS. Yes, so there is a close connection and there is close and continuous discussion really regarding availability of what's SABIC readiness and availability for CO2 and how much CO2 SABIC is planning to capture and sequestrate. So there is always a discussion with Saudi Aramco as they are the one who are really leading the CCS initiative in the country.
The electrification is also the both are doing together?
No. So electrification currently, we are developing the technology with Linde and PSF as our technology partners. But if this technology is successful, SABIC will be able to use it in the current assets, as well as there is also future opportunity for technology licensing also to third parties.
How about the hydrogen issue?
So hydrogen, as my colleague Salam presented, that we are planning to have it as either it could be our own technologies or also to work with partners or to actually source the technologies from partners. So we have all the options open regarding the hydrogen. Yeah, but yes.
Yeah, just if I may add, I mean, definitely there's collaboration with Aramco in these fields, and also there is a project now about ESMR, electrical SMR, and that's being conducted jointly by SABIC and Aramco. So there's quite a bit of work and collaboration.
So time is up, and this is the end of the question time. Thank you very much again. So next speaker is engineer Jalal Bushnem from Sonatrach. He has more than 20 years of experience in the energy sector and started his career at the Algerian Energy Efficiency Agency. He later joined Sonatrach, where he contributed to strategic planning in the oil and gas sector. He also headed the technical feasibility department and obtained the Green Hydrogen Expert certificate in 2023. Please get started.
アサラムアレイクム。おはようございます。私はジャラルです。よろしくお願いします。I'm honored to be with you here today to present the Sonatrach Energy Transition projects. As you know, Sonatrach is the oil and gas company of Algeria, a member of OPEC, a member of oapec. I will be presenting today the energy transition projects, mainly focus on renewable energies and green hydrogen, which are the subjects of the direction I work with. And then after that, we will go through some main technical issues to finish with the potential cooperation axes. We are working with some partners and still open to future partnerships. When speaking about energy transition strategy, there is here the four main axes. The first one is, of course, energy efficiency. We cannot speak about supply without speaking about demand. We should start first by a rationalization of the energy demand that goes through the energy efficiency. I can say that we have some actions, energy audits of our facilities, and we are aiming to get some ISO 50001 standards to be conform with the international standards. And the second most important subject, and which has big importance, it's gas flaring reduction. I can say that Sonatrach has joined the World Bank initiative for zero flaring by 2030, and we are working to reduce the gas flaring. I have seen yesterday a slide that shows some numbers of gas flaring. I can say that these numbers are under revision. We are started discussion with the World Bank, as it doesn't state the real state of the gas flaring numbers. I think there is no overestimation of the gas flaring, the real numbers of Algeria. We are working closely with the national agency, a spatial agency, to get concrete numbers. Then the last two axes, the green power for oil and gas facilities and the hydrogen, the green hydrogen mainly, we will be in details in the next slides. Starting from the renewables, Sonatrach has a strategy to integrate renewable power plants into its facilities to get some green electricity to feed its oil and gas facilities. So we are aiming to solarize eligible production sites. What do we mean by eligible? It means that there is some criteria we need to go through, and most of the sites are located in the south in order to, the aim is to reduce the environmental footprint and save natural gas and reduce the electricity bill for the operators. At the medium term, we are in the maturation phase for different solar PV power plants projects. And by doing that, we are going to, through a learning curve that prepares the basis for the development of green hydrogen projects. There is an optimization, of course, of CAPEX and OPEX that are the key performance indicators for such projects. I have mentioned some criteria that we should go through to build our solar PV power plants. As you know, the oil and gas operators care a lot about the reliability of the system. So we cannot just introduce solar. We are not allowed to disturb the functionality of the operators. And for that, we need to have the first condition, the availability of a natural gas pipeline. What do we mean by that? The aim of introducing solar is for saving gas. If we save gas, we need to evacuate it for gas export and to get value from that. And the second condition, the quality of natural gas. Sometimes in some projects we save gas, but it's not, it needs more treatment, and there is no close CPFs, central processing facilities, for the treatment to make it viable for export. And the third condition that goes with the reliability of the system, the availability of the national grid for system reliability. What do we mean by that? If there is disturbance coming from the PV system, there is always the availability of the national electricity grid that always gives electricity to the facilities. So in order to assess the potential capacity of solar plants, a detailed analysis has to be carried on potential sites in order to identify technical and engineering constraints. As you can see here in the picture, this is our first project that we implemented already. The performance of the project has exceeded the expectations. The solar PV plant has a capacity of 10 megawatts. It was implemented through a partnership with our Italian partner, ENI. It is located in BRN area, Berba Nor, and was commissioned in 2019. The plant covers an area of 20 hectares and it relies on monofacial solar panels. It allows to save about 5 million cubic meters per year of natural gas and avoid 10 kilotons of CO2 per year. During this year, Sonatrach is aiming to launch more projects using the latest panels technologies. Since then, the technology has got more advancements. And of course, grid stability with the integration of solar power is systematically studied. This is an ongoing project. It's not far from the first one. It also has a 10 megawatt capacity. As you can notice in the slide, there is an evolution in the technology we use. In the first project, we used monofacial panels with the capacity of the module of around 300 watt per module. Now we are using N-type bifacial with a capacity of more than 560 watt per module. Also, there is an evolution in the inverters we use. We increase the capacity to get more optimization from 42 kilowatt to more than 300 kilowatt. And for that, we can get an estimated energy production for the ongoing project that goes more 22 gigawatt for the same installed capacity compared to the 19 gigawatt hour we have now for the first project. I can mention also the Solar Lab. It's also has been done with our Italian partner, ENI. We have realized the PV testing platform. As you can see in the slide, the Solar Lab has the objective of testing different photovoltaic solar technologies under harsh conditions. What do we mean by harsh conditions? That a lot of our projects are situated in the south with high temperatures, which is not very good for solar PV, and also sandstorms. So the Solar Lab can help us to determine which are the best technologies for future projects, and set the optimal operation and maintenance procedures, and develop feedback from the testing these technologies. The second most important axis is the green hydrogen. It's a hot topic now. As you can see in the picture, Algeria has a lot of competitive advantages, and it's located near to Europe. And Europe is a big market for green hydrogen regarding their strategy of Repower Europe. They are planning to have like 10 million tons of green hydrogen produced in Europe, and they are planning to import 10 million tons of green hydrogen. Algeria has a high solar potential, an extensive national electricity grid with 99% electricity rate. Water is not a problem in Algeria because there is the experience of seawater desalination plants with more like 13 power plants already existing. And there is the possibility to get water for electrolyzers from the wastewater treatment stations. There is also an extensive pipeline network that we can use through repurposing to transport hydrogen. And there is also another advantage that we are already in the business of ammonia and urea, and it could be a good option to transport hydrogen. As you know, the main constraint of hydrogen is transport and storage. And we have like world-scale ammonia urea plants, like production of 4 million tons per year. Also 1 methanol plant. Sonatrach will work in the first phase to implement a program consisting of small-scale green hydrogen pilot projects. I can say that Algeria has got its strategy of promoting green hydrogen recently, and the Sonatrach strategy is aligned with the national strategy that goes first with the pilot project phase. Then after that, we go to semi-industrial products and export at long term. So the first phase consists of pilot projects in order to test technologies for the production and applications of hydrogen and develop expertise in the entire value chain from production, transport, storage, and applications. In the second phase, we will go through industrial and commercial green hydrogen projects that will allow to evaluate different business models and transportation routes. What do we mean by business models? We have mentioned a lot that green hydrogen is expensive now, but it was the case in the past for renewable energies, and with incentives from the government, with the different innovative business models, we can have real concrete projects, especially off-takers of green hydrogen. We have started to identify some projects, as you can see in the picture. The first one is supposed to be in Arzo area, is in the north. I have started by the project 3. It's a Power-to-X project with an electrolyzer capacity of 50 megawatt. It is supposed to be generated from a hybrid generation of electricity. Why hybrid? Because it's the best way to have more hours of functionality of the electrolyzer. The solar PV combined to wind. We have another project in the south region. As I have mentioned before, our aim in the long term is to export to Europe. The national strategy have an objective of 1.2 million tons at 2040, which represents like more than 10% of the Europe market. And to test the feasibility of transporting hydrogen blended with gas is the subject of the second, the project number 1, which is situated here second in the slide. It's a pilot project to test the transport of hydrogen and also a buffer storage to see the behavior of the storage also. We can also test not only blending, we can also test repurposing existing gas pipelines to see the possibility if we can transport hydrogen in existing gas pipelines. Another pilot project which is ongoing in partnership with our partner, Italian partner ENI, is introducing hydrogen into power generation gas power turbine. The idea is if we can introduce some hydrogen in existing turbines without modification So there is a possibility to replicate the projects at a larger scale, at a national scale, even with our national operator of electricity and gas. The main technical issues we are facing first in renewables, we have the grid stability. As you can see, the solar PV is intermittent, and we cannot allow the integration of solar PV without doing a grid stability study. And then introducing battery storage have not only a technical issue, but the possibility of getting an economic project with the battery storage. Trackers are not yet tested in Algeria, but we are focusing on this solution because it brings more production and it gives more profitability to the project. So we are considering trackers for the future projects. And the new panels technologies, we have seen a rapid evolution of the panels. With the N-type, we are testing in our second project, but there is other projects that are supposed to be more efficient, like heterojunction, and the adapted foundations. Sometimes we find difficulties in getting adapted foundations in the south because there is sand, and if we want to get solar power PV, we need to have stable earth. So there is maybe a need of innovation to get adapted foundations for that. For green hydrogen, as I mentioned, we are willing to test blending and repurposing possibility to transport hydrogen, and test also other possibilities like the liquid organic hydrogen carrier. I have mentioned also that it's optimal to have a hybrid green electricity source, solar PV with wind. And it's not excluded that in the future we will study also the methanation perspectives. I mean, the CO2 combined with hydrogen to get synthetic gas. From that, we are working with our partners on these main potential collaboration axes. It's for both renewables and green hydrogen. We are working on the technical assistance, on feasibility studies, on front-end engineering designs, and capacity building, as human resources are the core element of each strategy. So we are focusing on capacity buildings, on technical issues. And what is specific about renewables is grid integration and power management issues. What is specific for green hydrogen is the technical aspects regarding transport and storage options. Thank you.
Thank you for your presentation. And we have 2 minutes, so does anyone have any questions? Please.
Thanks, Jalal, for the interesting presentation, and it's really very useful to see your strategy for green hydrogen. I just have maybe a different type of question. In your strategy, do you consider, for example, the decommissioning and recycling of these PV modules? Because it is one thing to have a 10 megawatt solar station to produce green hydrogen, but when you have many of these, this could become in 25 years when the lifetime of these solar panels expires, could become a big problem in terms of what do you do with them? Is this part of your plan? For example, are you thinking about maybe having some kind of recycling facilities in Algeria, or maybe shipping these overseas for recycling? Because it becomes obviously, is it part of the economics? When you look at the economics of producing green hydrogen, that would be an additional cost, first of all, but also an additional environmental impact.
Thank you for the question. It's a very important aspect that we should consider in the future. But until now, we are in the first beginning of our projects. Not only Sonatrach, but also Sonalgas as the operator of electricity and gas. And they have launched lately like 3,000 megawatt of power plants. So until now, renewables is not have not a big ratio of the electricity mix in Algeria. But of course, it's a very important aspect that we can consider in the future by going through maybe recycling the power, the panels in the future.
So any other? Okay. I want to move to next presentation. Is okay? Thank you very much again. So next is the final speaker, engineer Omar Badros from SABIC. He has a bachelor degree in chemical engineering from Royal Abdulaziz University and has 15 years of experience with SABIC. He has worked mainly in the olefins business and after 2023 is leading the deployment of new chemical technologies and internal development technologies in the MEA region. He leads decarbonization projects, circular economy projects, and technology development into chemical products. Please get started.
Assalamu alaikum. Good morning, ladies and gentlemen. Thanks. I really appreciate the organizers for this symposium, for having this great symposium and sharing all the information. And I'm glad to be here with you to continue the speech that's being started by my colleague Uthman and the rest of the team here. So I will continue this with the carbon capture for the first adapter. So we'll go through this agenda. So we'll start with the introduction. So as mentioned by my colleague Salim, that we are looking for the steam crackers because in SABIC we have a huge amount, almost 20% of the CO2 emitted from the SABIC assets, around 20%. And globally, for the petrochemical industry, it is around almost 16% that emitted for the CO2 especially from the steam crackers. For that, we are looking especially deep on the steam crackers, how we can reduce or avoid the CO2 emission. So SABIC having several solutions or technical solutions for that, and they are working on those solutions, as mentioned yesterday by my colleague Uthman and today by my colleague Nasser, about the reliability and energy efficiency, renewable energy, electrification, carbon capture, and the green or blue hydrogen production. So now the carbon capture plays a crucial role in SABIC to achieve the 20% reduction by 2030 and to be a carbon neutral by 2050. So again, to the same slide that been presented by my colleague, why we do have the first adapter. So most of the technology yet not proven commercially, mainly for hydrogen and electrification. And for the CCS, it is there. But especially for the furnaces, or the steam cracker, yet it's not commercially proven technology. For that, we have came with the first adapter concept to prove those concepts and those solutions for the decarbonization and gain the operation and engineering experience for that, and also make sure that our asset will work in a good reliability, because if we lost the reliability, the CO2 emission will be increased and the greenhouse index will be increased. So this is a normal carbon capture overview that we do have the adsorbent columns and separation column, but the most difficult part, which is how to connect it direct to the steam cracker stack. So to connect it to the steam cracker stack, directly to the CO2 absorber unit, this is where we have the difficulties and the challenge. So we'll talk about mainly, we'll focus now on the carbon capture for the first adapter for the cracker. As I mentioned, that this technology solution, it is already commercially available. But for the steam cracker, not yet, with the huge amount of the CO2 that's coming emitted from the steam crackers. So we went to this exercise to de-risk this technology, since the furnace, the steam crackers, as most of you know, that it goes dramatically through different mode of operation: startup, decock mode, down cold mode. So there are several modes that the CCS unit will face during their connecting to the steam cracker. There will be a high energy demand for the CC unit, and the concentration of the CO2 coming out from the flue gas, it's having a low concentration, and the CC unit will require a huge plot plant to be considered there. So as mentioned, this is how the different mode of operation for the steam crackers, and each one, it has its own flue gas concentration. So during the normal operation, we will have, we'll have the flue gas with the high CO2 from the combustion of methane fuel gas. And during the decock mode, we will have also a huge amount of steam coming back to the steam cracker, if we will have the direct decock flow going back to the firebox, and also with some particles of coke that's going back inside the firebox again. And during the hot steam standby, that we will have a huge amount of steam coming back to the furnace itself. So, as mentioned by my colleague Salim, previously we do have a lot of amount of and different numbers of steam crackers in each plant. So how we can gain our experience, and how we can select, shall we select one furnace or two furnaces, or the full unit to be sent the flue gas to the carbon capture unit, or several furnaces from that steam crackers. Some of the crackers we do have, it has around 10 furnaces, some of those 7, some of those 12. So we need to know and gain the experience and prove the concept and the timeline for us to complete this project with the low capex for sure. So we went through this study to see each option that we do have. So if we do one furnace only, we will prove the concept, but we will not gain any engineering experience or operating experience during the different mode of the furnaces. It will be fast and with the low capex. When we go with connecting two stack of the furnaces to the carbon capture unit, we will prove the concept. We will gain the engineering, because one furnace will be on running mode, the other one will be maybe in decock or on down cold mode. We will gain the operating experience for the CCS unit. It will be fast also, and the capex will be on the higher side a little bit. if we go with the several furnaces, we will face an issue in terms of the capex and the timeline for implementing this project. For the old furnace, for sure, we will require to have a shutdown or turnaround for the plants in order to complete this exercise. For that, we recommend to go for the first adapter to prove only the concept of this technology. It's to go with at least 2 furnaces. So one furnace will be on the running. If both are going to the run mode, we will see the impact on the CCS unit and what will be the impact on the absorbance of that carbon capture unit during going to different mode. If we are going with the low feed, what will be happen to that carbon capture unit. So another challenge that we are anticipate to face during this first adapter, which is the energy requirements for the carbon capture unit. As you all know that for the carbon capture normal unit, there are condensers, there are reboilers, the regeneration for the carbon capture unit itself, which having a high demand of energy required. So we are doing a carbon capture for the furnace itself, but the energy required to operate the CC unit itself, it will increase our carbon footprint at the end for the whole complex. So this is one of the challenge also. The other challenge will be also for connecting the stack, which will require kind of blowers for to connect it to the CCS unit. So there will be a huge demand in terms of the energy required for the carbon capture unit. So we are seeing that we can utilize an e-boilers and condensers to be utilized here, but we need to have it also from a renewable energy to maintain our carbon footprint for the complex. So this will be my last slide. So many people, they are talking about the CO2 sequestration and CO2 utilization. All we know that there are 2 ways of the carbon capture, either to sequestrate it in the wells, and that will be depend on the availability of those wells in the region and how we can transfer that CO2 to those wells with if we do have a facility for the hubs to utilize there, how much the quantity and the capacity, also the concentration for the CO2 to be utilized there, the CO2 being captured. So there are several concerns and challenge on that. So long-term stability of the CO2 storage, SATs, as CO2 leakage could impact the environment also. Limited availability of the suitable CO2 storage sites and low project feasibility due to a high cost of the decarbonization unit. And this is another challenge which is impacting the plants in order to execute or implement the carbon capture unit. For the utilization, the same, the requirements for the energy, and you have to have kind of infrastructure for producing low carbon methanol or urea, also availability of the renewable energy for the hydrogen. So in order to say that you have a low carbon methanol, the technology maturity of producing the green hydrogen and availability of the hydrogen, and how we can achieve the low carbon methanol, and also the feasibility study and project high cost that will impact our, let's say, some of the plants' decision to go with those kind of CO2 capturing. By this, I end up my presentation. Thank you.
Thank you for presentation. We can have one question. So does anyone, okay, please. Oh, sorry.
Assalamu alaikum. Good morning. Thank you for the excellent presentation. Salih Al-Ghamdi from Lubrif, Environmental and Sustainability Team. Regarding the CO2, the carbon capture facility that you aim to, not the last chapter, the one before it. Can you shed the light about some of the figures? Like how much capacity you aim to capture, the condition of the low pressure steam in terms of pressure and temperature, if those information are available. Just to help draw a picture about the requirements in the future for other companies. Thank you.
Thank you for your question. And it's a great question. So we say that for the current first adapter, we are aiming to select only 2 furnaces for capturing the flue gas. And those conditions will be different from site to site because the amount of flow gas that going out from the firebox is different, depend on the capacity of the furnace itself. Other aspect, which is the concentration for the CO2 coming out from that furnace. So it is differ from plant to plant. There is no solid answer for that. For the steam requirements, mainly it is an MP steam with the pressure around 500 kPa, 500 kPa. So that's about the required steam.
Thank you so much.
Thank you very much for your talk. I have a question about the nature of the material inside the carbon capture unit. The nature of the material inside the carbon capture unit. And does it need regular regeneration? I mean, what about the lifetime of this material? Thank you.
So it is an amine absorbent material, and the regeneration will be depend on the quality of the flue gas. So yet we are in studying those kind of things and the concentration and the impurities that coming with the flue gas from the furnace and how much will be the regeneration cycle for that.
But it can be reused. I mean, this material can be regenerated and reused for certain number of time.
Yes.
Okay.
Sure.
Thank you very much.
Thank you. Oh, okay. Last question. Okay.
Thank you so much. Thank you for answer my question, utilizing of CO2. Thank you so much. I have a question as an inquiry. Do you mean use of heat of free gas instead of heat of steam in steam cracking? Yeah.
Can you repeat your question?
In hydrocracking, we used in refinery steam for hydrocracking or cracking. Yeah. Your research or study or suggestion used heat of flue gases instead of steam.
Okay, so we are talking about the steam crackers, which is for the olefins plants.
Yeah.
So normally
in refinery.
Not in refinery, in the petrochemical.
And
in the petrochemical. So normally the furnace.
We have flue gas in furnace.
Yeah.
We can use as combined cycle in electricity generation, steam turbine and gas turbine, for example.
Yes.
A same idea.
I didn't get the questions to.
in hydrocracking or cracking, steam cracking, we use steam. We have boiler to generate steam.
Yes.
With high potential energy, heat. We use this heat in steam to hydrocracking or cracking. Yeah?
Yeah.
Your suggestion, instead this steam by flue gases, because flue gases have also heat, high heat and temperature. This your idea or other?
Salim.
Yeah.
Well, I think here in this project, we're talking about capturing CO2 from flue gas. So flue gas is a result of combustion of mainly methane as a fuel. Yeah. So we're trying to capture the CO2 from the flue gas. It's different than the concept of adding steam to the hydrocarbon for steam cracking. This is in the combustion side.
Thank you so much. Thank you.
Thank you very much. And the last question is with Chat. What the actual projects that are actually implemented in SABIC in the field of hydrogen combustion and carbon capture? Okay.
So the question about what's the actual project for hydrogen combustion implemented in SABIC. Actually, the project is still in progress. We have not completed the project yet, but we're working on that. It's in the study phase, and all the technical challenge has been shared in the presentation.
And just to add on that, all the three solutions, we are working on it on the same speed, on the same time. The electrification, the hydrogen combustion, and the carbon capture project. So all of them are on the fields now. We are going with the same speed to be under study.
Thank you. Thank you for all speakers and participants. And that's all, session 5. And at last, award and take photos.
Thank you very much. We have now a short coffee break. Please come back in 11:50 because we will have the last session and we want to be on time, inshallah. Your feedback is very appreciated. So we have a barcode on the table for the survey. Please follow it and give us your feedback. Thank you very much. Bismillah ar-Rahman ar-Rahim. Everyone, please let us start the last session because of the time. Now we will start with the session entitled Initiatives and Efforts to Reduce the Carbon Emissions. The chairperson is Dr. Nasser Auda. Please, Dr. Nasser.
Thank you. So this is our last session for today. Again, it's basically looking at initiatives for reducing carbon emissions in downstream operations. And so looking at different aspects and different proposals, maybe different case studies. So the first one we will start with is from Sonatrach. And basically we have Mr. Sassan is the head of CDU department at Skikda Refinery with over 14 years in refining. He graduated from National Hydrocarbons Institute. In 2008, he joined Skikda Refinery as a process engineer and worked in various units, including utility and effluent treatment. He was promoted to head of the production department in 2022 and specializes in technical support and refining troubleshooting. So looking forward to listening to your presentation, Mr. Sassan. Please go ahead.
Thank you very much, Doctor, and good afternoon, everyone. Before unveiling the content of my talk today, I would like to address my warm thanks to the scientific committee, as well as the chairman of this symposium, for giving me the opportunity to participate in this valuable event, treating a very important oil and gas relevant issue, which is triggering large discourse and escalating concerns. Sonatrach's strategy is fully committed to environmental protection and has set the objective to reduce flaring gas reduction. Firstly, I'm working in operations where we manage petroleum refining facilities, and we focus on optimizing unit operations to maximize production, minimize costs, and maintain products, specifications, and safety, personal safety. In this regard, I'm extremely thrilled to share with you all through my presentation entitled Skikda Refinery Flour Gas Recovery System, our current event, and our vision, as well as the future action plans deployed by RPC to mitigate the carbon footprint and to align with Algerian commitment for reducing the gas flaring considered as the main source of the carbon emissions in the petroleum downstream industries. So this is the content. Starting with the resumed overview of Skikda Refinery, which is considered as the largest refinery in Algeria with total capacity reaching 16.5 MMTPA. The Skikda Refinery is producing a large spectrum of derived products such as LPG, fuels, petrochemical naphtha, aromatics, and bitumen. For that, it contains different units and facilities which are represented in this table with storage capacity more than 3 million cubic meters. As a petroleum plant, Skikda Refinery is equipped with flour gas system gathering the off gas released from different units and collected in a piping header before being delivered to flour system for safe disposal. Briefly, flours are combustion devices designed to burn surplus or waste gases generated in oil and gas plants safely and efficiently. In other words, flours are safety devices that prevent the release of unburned gases to atmosphere, which may burn or explode in presence of an ignition source inside or even outside the plants. From operational point of view, there are mainly two levels of flaring. The first level is flaring, which takes place in case of equipment failures, emergencies, planned and unplanned shutdown. For this level, the flow rate of gases can be used in short duration. The gas flow discharged to the flour system determines the flour hydraulic capacity. The second level is flaring, which takes place during the normal operation, including but not limited to process gases, fuel gas, purge gas, sweeping gas, and valves, safety valves connections. For this level, the flow rate is much lower than the first. Gas flaring is one of the top world energy and environmental the world is facing nowadays. Meeting energy demand will not require just producing more, but also using what we produce more efficiently. In Algeria, efforts have been done to tackle the flaring gas problem, taking into consideration the expectations that gas flaring will be not allowed in the near future. So, Skikda Refinery was implemented to reduce flour gas emission FGR to minimize energy losses, optimize cooling process using reciprocating compression. This FGR contributes significantly to emission reductions by reducing combustion emissions, including NOx, SOx, rationalizing fuel gas consumption, reduce flaring light, noise, and odor, minimizing steam consumption, extending flour chip life, no impact on existing relief system, improve revenue and company image. Skikda Refining is adopting a classical flour recovery system, which is highlighted in this PFD schema, where the excess gas is coming from the crude distillation drum to flour gas compressor drum, and will be compressed via reciprocating compression, cooled, and the liquid is recycled to the naphtha stabilizer column. It's noteworthy to mention that the existing system permitted to get a recovery rate of 56.25%. But it's not satisfaction for Skikda Refinery because our target is to attain a total recovery and seizing all fluorine-related aspects. As a part of refining and petrochemical plants, Skikda Refining is recording the highest level of fluoride quantity, reaching in 2023 71,027%, which represents 69.5% of the total RPC fluorine gas. With our FGR and the Science 2011, we have made a reduction of an estimated rate of 44.51% during 12 years. The fluorine tax, Algerian legislature put in place bonding provisions, emitters, requiring emitters to pay fluorine tax. For RPC, it's more than $11 million. This table is showing the annual level of treatment of our refinery, as well as corresponding fluoride gas. We note that during the last 3 years, a huge reduction has recorded where the rate was 0.83% in 2011 against 0.35% for the last years, despite the increase in capacity production of our refinery after the project renovation during 2012. Regarding this fluorine tax, despite this huge reduction, where is estimated more than $6 million, implying large losses rather than be saved and invested elsewhere. Here we have RPC effort to mitigate the gas fluorine. The refining and petrochemical downstream activity has implemented a strategy aimed at significantly reducing the quantity of fluoride gas by respecting the admissible threshold for the gas fluorine rate fixed at 1%, setting fluorine rate performance target to 0.33%, maintain equipment integrity to technical international standards, maintenance plans, and replacing the energy guzzling equipment, carrying out energy audit, and adoption of ambitious investment plans for FGR. So the technical solution proposed is based in the use of liquid ring compression with 2 stages. It's used in over 90% in the world. The advantages require less maintenance, reasonable cost, operate even with the 2-phase load, no need to install knockout drum or gas scrubbers, low speed operation, the heat of compression passes into the operating liquid. The capex of one module is $9 million, so the flaring tax paid per RPC can purchase one module for our refinery. And finally, we have a RPC global approach with the ultimate goal for reducing and mitigate the flaring gas by actions in the short term and medium term. So in the short term, zero flaring by 2025 for our refinery, zero flaring by 2026 for petrochemical plants, and the medium term program for the other units. Thank you very much for your attention.
Thank you, Mr. Sassan, for a very useful presentations. Yes, I mean, recovery of flare gas and, you know, addressing methane emissions is important, something which obviously we always need to talk about whenever we talk about, you know, oil and gas industry. I mean, obviously this region is known, very well known for meeting, obviously reducing methane emissions, Saudi Arabia and region as a whole. Does anybody have any questions for Mr. Sassan at this point? Yes, sorry. Yes, please.
So the existing is mounted by Brown Root Condor, BRC.
Skid mounted.
What?
Skid mounted unit?
Yeah, skid mounted. So the particularity is mounted only inside the crude distillation units. For the other units, like gas plants or reforming, there is now FGR recovery. So our new investment, inshallah, will be make this liquid ring compression in the principal header of our refinery. Oh. Yeah, for the targeting is total recovery.
Thank you.
Any other questions? Yes, please.
Yeah, thank you. All the time, the flare gases doesn't have uniform quality. So how do you manage this process? Because flaring can be from different sources.
Yeah, this is what explains the rate of 56.25. The rest is reused for our boilers and furnaces, and the excess will be sent to flare system. And this is what it's our institute plan to mitigate all flared gas inside our refinery.
Yes, any more questions? Okay, in that case, let's move to the next presentation. It will now be looking forward to listening to the SASREF decarbonization roadmap from engineer Mohammed Al-Shahrani. Mohammed joined Saudi Aramco Jubail refinery in 2018 as a process control engineer. From 2023 until now, he is a senior production planning engineer. He holds bachelor's degree in chemical engineering from King Fahd University of Petroleum and Minerals in 2017. Mohammed, please.
Assalamu alaikum. Ladies and gentlemen, good afternoon. As Mr. Abdul Al-Karim here has already said, that my name is Mohammed Al-Shahrani. I am a senior production planning engineer in SASREF Refinery Company. I am very grateful and thankful for this opportunity to share with you SASREF Refinery roadmap towards decarbonization. Now, at the beginning, we all know that greenhouse emissions are one of the major crises that affects humans and their environment. It has a major impact in our planet's weather and climate system, such as global warming, shifting of wildlife, and raising of sea levels. For that reasons, SASREF has an obligations toward the society and the environment to raise the concern and also to take some initiatives that will contribute directly to the reduction of greenhouse emissions for a clean environment. Now, just before we start, I just want to share with you a disclaimer statement that shows that any information that's been used here is solely for the purpose of this discussion. Any use of such information should be with the permission of SASREF. Now, at the start of our discussion, and before we go through our main subject of this presentation, allow me to briefly share with you an overview of our company, SASREF. SASREF is a short term for Saudi Aramco Jubail Refinery. It is located in Jubail Industrial City, which takes place in the eastern province of Saudi Arabia. It was a joint venture refinery that was owned by Saudi Aramco and Shell Company. And that was up until 2019, when we became 100% owned by Saudi Aramco. SASREF Refinery is receiving from Saudi Aramco an average daily rate of 305,000 barrels of Arab light crude, which is being processed through some major units in SASREF, such as crude distillate units, hydrotreaters, and some complex units, such as hydrocracker and thermal gas oil unit. Now, it's also worth to mention that SASREF main fuel productions consist of chemical feed naphtha, jet fuels, gas oil, and also fuel oil. Now, when we talk about SASREF decarbonization strategy, we need to understand the motive and the drive for such strategy. SASREF is striving to contribute to the reduction of carbon emissions toward a cleaner environment. These contributions comply with Saudi Aramco strategy to reach a net zero target by 2050. Now, all of these strategies of SASREF and Saudi Aramco falls under the vision of our nation to reach a net zero target by 2060. Now, one of the critical steps to achieve such target is adapting the circular carbon economy. Now, as you know from those seminars today, here, and yesterday, that circular carbon economy is a framework for managing and reducing CO2 emissions. It is a closed-loop system that involves the famous 4 R's. The first one is to reduce, and from its name is by reducing CO2 emissions. And the best examples for such activity is by improving energy efficiency and flare minimizing. The second one is reuse. That is when we captured CO2 to reuse it as a useful product, such as fuels, bioenergy, and chemicals. The third one is recycle. And that is when we chemically transfer CO2 into a whole new substance, such as fertilizer or cement. And finally, remove. That is when we use technologies to capture the CO2 and store it to achieve a large-scale reduction of its emission. Now, on the road of developing its roadmap, SASREF has listed all the key items that will help to shape its strategy. Now, the first step to develop any strategy is by defining your baselines. Our baselines helps us to assess and evaluate our position of CO2 emissions. It benefits us to direct our focus towards the main contributor for such emissions, and also it is a critical tool to measure the progress toward our target. The second step is by setting your realistic target. This was developed by evaluating the possible opportunities that will be captured in the upcoming years and the magnitude of their impact on our baseline. The next key item is developing what we call an emission abatement prioritization matrix. In this matrix, we set all the processes and their contribution to the CO2 emissions, along with the opportunities and the solution to reduce those emissions. Then each opportunity will be evaluated based on their visibility of each process in order to prioritize our initiatives. Now, once we set all the initiatives, we then evaluate them economically and evaluate their cost and their impact on our refinery. This can be done by developing what we call the technical marginal abatement cost. Now, once we evaluate all the opportunities and completed their evaluation of their priority or for their feasibilities and their cost, we now align a short and the long-term decarbonization initiatives, and also align them with our business strategy plan for the year. Now, and finally, after setting all the plan and complete all full evaluation of the strategy, we start implementing those initiatives and measure the progress towards our target. Now let's go through them one by one, and the first one is defining a baseline. SASREF has successfully developed a baseline of total emissions for a strategy, which took place in the year 2022. At that time, we had a total emission of almost 2.11 million tons of CO2 equivalent. As you can see from the chart ahead, that most of those emissions comes from the process side. So the first hint for us was to direct our focus on that area and evaluate the possible opportunities to reduce its emission. The next step is to setting a target for our plan. By evaluating the solution can be captured in the upcoming years and estimate the impact of our emission, we managed to develop a target reduction of 5% of our emission, which is equivalent to 0.15 million tons of CO2 equivalent. That will be implemented, hopefully, inshallah, by 2035. Moving forward to the next step, which is developing what we call an emission abatement prioritization matrix. In this matrix, we have successfully managed to list all the processes that led to CO2 emissions in SASREF, such as flaring, venting, process heating, and hydrogen generation. We also list down all the potential opportunities that have been inspired by the circular carbon economy frameworks that will help to reduce the emissions of those processes, which is, for example, improving energy efficiency, using renewable sources, and also carbon capture technologies. Those opportunities are shown ahead have been arranged based on their maturity. So the ones on the left side are the short-term range initiatives, or as we call them, the low-hanging fruit opportunities, while the ones on the right are called the long-term range initiatives. Now, going along with each opportunity, we measure and evaluate its feasibility to be implemented in SASREF. The ones that are preferred to be implemented for each process are highlighted in the dark blue color, while the ones that are less preferable to be implemented for each process are highlighted in the light blue color. And of course, the ones that are with no color are not feasible for each process to be implemented. Now, by looking across this matrix, we can clearly identify and prioritize all the potential initiatives for SASRF to reduce its emission. Now, as a result of that, we managed to come up with a firm strategy execution plan to 2035, which includes 3 major initiatives, each one followed by a minor steps to help to fit the purpose of such initiatives. Now, to go for the first one, which is energy efficiency improvement, this initiative is completely being assessed and evaluated by our technical and engineering team, and we came up with a plan that contains such steps to reduce the energy losses and increase energy efficiency. Those steps such as upgrade heat exchangers, improve insulation, and optimize operating parameters. Now, the second one is carbon capture, utilization, and storage. And that is when we use synergies when we synergize with a neighboring company to capture and export our CO2 in order to produce what we call the blue hydrogen. This is going to be illustrated next in the upcoming slide. The next step is to examine and certify produced fuel for low carbon intensity. Now, this step has been already successfully implemented in SASRF, and we can proudly say that most of our production are considered to be low carbon intensity products. Now, the third one is to evaluate flare gas recovery system. We hope that this flare gas recovery system will help us to minimize our flaring to reach what we called zero routine flaring. We hope this is going to be implemented in the nearest future. The third one is we consider it as a long-term initiative, which is using renewable energy sourcing. This can be done by cooperate with green power producer and align with our neighboring company to share and use green power sources. Now, as we said here, that one of the major milestones that have been implemented in SASRF is producing a blue hydrogen. Now, in the past, SASRF used to produce what we called a gray hydrogen. For those who don't know the difference between a gray and blue hydrogen, gray hydrogen is when we process steam and methane into our SMR unit, which is a steam methane reformer. This is to produce hydrogen, but unfortunately, one of the byproducts of such process is venting CO2 to the atmosphere. Now, that was the case in SASRF up until 2020, when we came up with an idea to utilize our CO2 to synergize with a neighboring company called Sipchem to utilize our CO2 in their methanol plant to produce methanol. This allows us to be certified for producing a blue hydrogen in 2020 and 2022. SASRF has been certified for producing almost 8,000 tons of blue hydrogen in 2021. Now, it's also worth to mention that this certification is considered to be first of its kind in the whole world, that's been given by a third party called TUV for producing a blue hydrogen in SASRF. Now, lastly, is worth also to share with you some of our low carbon fuels production. SASRF has successfully been certified for producing low carbon intensity products such as low carbon aviation fuel and low carbon chemical feed naphtha. We have been certified for those two products, but also we are in the progress of certifying our low carbon fuel oil, and hopefully in the near future we will be certified of our fuel oil production for having a low carbon intensity product. Now, at the end of my presentation, I would like to say that despite what we have already done and what SASRF is planning to implement in the near future, we are confident enough that this is not going to be the end of our journey. This is actually the beginning of the road to reach our net zero target locally and globally. And we know it's not going to be easy. We know also it has its challenges, but we also always need to ask ourselves, what can we do more? And what also ambitious us to look for more initiatives to reduce greenhouse emissions for having a clean environment and better life. Thank you so much for listening. If you have any question, I will be happy to answer it. And if you have any question, please reach me at any time. I will be happy also to answer it. Thank you so much and have a good day.
Thank you very much, Mr. Muhammad. It's really an amazing journey, and the strategy is very, it's a great strategy. I think I very much like the prioritization approach, and basically the matrix you showed. It's realistic, transparent, and also your certification, strategy is also, I like that. I think I also like the fact you showed the circular carbon economy, the 4 blocks, the 4 Rs. And I just want to emphasize here that when we talk about the remove within the circular carbon economy in Saudi Arabia, we talk about removal. We don't talk about reduction. We're not talking about fossil fuel with carbon capture. We're talking about, for example, biomass with carbon capture. We talk about direct air capture. That is really the remove part of the circular carbon economy. Just to emphasize that. And does anybody have any questions for Mr. Muhammad? Yes, please. Yeah.
Thanks for your very interesting presentation about your SASRF's strategy and plan. And my question is about a very specific question about carbon capture on your SMR. In your presentation, you said that from the previous gray hydrogen in SMR, and by implementing the carbon capture, that will become the blue hydrogen, and CO2 will be used for the methanol production. So I guess from the SMR, the reformer furnace, the carbon dioxide from the flue gas, reformer furnace flue gas was captured. So my question is, what kind of technology did you apply to capture the carbon dioxide from the reformer furnace flue gas? I think that is very challenging technology. Thanks.
We are utilizing our CO2 and send it to our neighbor company CO2. So we are not capturing and storage it, but just utilize it and sell it to a neighbor company, which is SIPChem. We are using our SMR we are capturing CO2 in our SMR unit and then sell it back to SIPChem for the methanol plant to produce a methanol. It's not actually capturing and storing CO2. Yes, exactly.
Thank you for the question, the answer. Any other questions? Yes, please, yes. No questions, okay. Okay, then in that case, we can just go to the next very interesting presentation from Mr. Abdulaziz Talal. It's on vent hydrogen recovery utilization. Mr. Abdelaziz is a process improvement leader at Sadara Chemical Company since September 2018. He's responsible for improving processes and efficiency. He previously worked as a process engineer at Crystal and began his career with Crystal, home to a titanium dioxide complex situated in Yanbu Industrial City. He worked there as a process engineer for more than 4 years before joining Sadara. He holds a bachelor's degree in chemical engineering technology from Yanbu Industrial College. Looking forward to hearing your presentation, Abdelaziz. Thank you.
Yes, Assalamu alaikum. Good afternoon, ladies and gentlemen. Just before I start my presentation, I was actually quite impressed by our guests and colleagues from Japan. They came here and they tried to greeting us by our language. So it was really positive and good attitude, and we are not expecting the less actually from a great nation like Japanese people, so really appreciated. And I want to follow the steps of Mr. Jalal, what you have done today. I have tried to learn something from my end. I hope that I'm saying it correctly, and apologies if I'm doing it wrong. So, konbanwa, watashi wa Abdelaziz Malaib, improvement leader in Sadara Chemical Company. Yoroshiku gozaimasu. So today my topic is actually to discuss about the vent hydrogen recovery and the utilization within Sadara Chemical Company. But before I start the topic, first of all, I will just go through Sadara. So I will explain what is Sadara, and then I will go in detail about the abatement categories which is applicable to Sadara Chemical Company. Then I will explain about the different initiatives that were implemented, and also which will be implemented for the same strategy. Then I will discuss. Then I will go in detail a little bit in my topic, which is the recovering of the vent hydrogen. So first of all, what is Sadara? So Sadara, by name actually and definition, is to be upfront. So this is in Arabic language. Sadara always to be in the first place. And this is what we hope always to achieve and maintain. And this is also the expectation from our stakeholders, Saudi Aramco and Dow Chemical companies. So Sadara, it was established in 2011, and it was fully commissioned and came into production in 2017. It passed the CRT test by end of almost 2018. So we are still new to the market, a new company. We are learning. It's a good opportunity that I'm being here to learn from all of your experience and long journey. So this is about Sadara. The whole project, it was the biggest complex that was ever implemented in single phase. So it's a very huge complex. It was done in single phase with over $25 billion investment. So we have in our complex, we have almost 26 manufacturing plant and technologies. 14 out of them, it's a new technology to the kingdom. We have the only mixed feed cracker within the Gulf region, which have the flexibility of the feedstock between the gas and liquid. And it can produce over 3 million metric tons of commodity products, which is in daily use of almost everyone. So in plastic, we can see it in our glasses, sticks, and also in foam industries, in our shoes, sofas, and chairs. So this is how almost Sadara is contribution. And to discuss about the most important asset, which is the Sadara employees, and this is the most valuable asset. We have almost more than 3,000 employees within Sadara with 30 different nationalities. So this, we can say how a multinational organization always seeking for the talented people who really add value to the organization. 76% out of them are Saudis, who are using their knowledge, minds, and the hard work to operate the plants, and also always we are empowered the female within our organization. So this is just a brief introduction to Sadara. So most of you, I hope that they are familiar with currently. So regarding the abatement categories which is applicable to Sadara. So first category, we have the efficiency in the process technologies. So by this one, we are focusing on improve energy efficiency through business as usual initiatives as to be implemented of the new technologies and the most effective technologies across the production processes. The second category, which is low carbon heat, is to substitute the current fuel with the lower carbon heat, and we have one example. Those first two areas, actually the Sadara focus currently and what we are working on from implementation perspective. And then we have the third, fourth, fifth category, which is renewable power and energy, carbon capture and offsetting. This is the future plan where still it's under study phase, working with our neighbor companies, with third parties to finalize the studies and also to define the implementation process and how we can move it forward. So regarding decarbonization initiatives and strategies, so the completed and implemented projects, we have almost 13 initiatives. It was a soft change, zero investment. It's under efficiency and process optimization. Almost we have captured 99 kilotons of CO2, and this is already completed. We have another 5 initiatives. It was with the capital investment. It's a project. Also under the same level for efficiency and process optimization, we were able to capture 108 kilotons of CO2 per year. So this is almost what we have captured so far, more than 200 kilotons of CO2 per year. And what is on the downpipe of the road and which is in the progress for implementation, we have another additional 3 soft changes without investment, still also under efficiency and process optimization. This is equivalent to 32 kilotons of CO2 per year. And we have 14, which is required investment, ongoing initiative, under low carbon heat, plus efficiency and optimization. So this is around 275. One specific, and it's a major project, which is switching the boiler from fuel gas and HFO as a mix to have it 100% shale gas. So this will help us to reduce 100 kilotons of CO2 per year. So you can see as a total, maybe we can reach more than 600 kilotons near future, inshallah. And this is only for the first 2 categories. The remaining, it will be all captured by the other abatement categories, which is the renewable carbon capture and offsetting. So Sadara is working diligently with on many efforts, including the power efficiency enhancement, carbon capture and offsetting. And all of this effort is to achieve the zero net target in line with our stakeholders' actually expectations, plus also in alignment with the Saudi vision for sure. So regarding my topic for the vent hydrogen recovery, we have a chloroalkali plant within Sadara Chemical Company, which is well known for production of chlorine gas, plus caustic as a secondary product, and mainly you will have hydrogen as a byproduct. So this is the general chemical reaction. As per the design capacity of the electrolyzer, it was decided from the design phase, the quantity of hydrogen is minimal, and it will be a very huge expensive if we want to capture it and utilize it. So it was decided to be vent to atmosphere, and this is from design phase. And currently we are venting it to atmosphere. So the proposal is, since as per best industry practice, the hydrogen, it can be utilized either for production of 32% HCl, or it can be utilized as a fuel. Within internal synergy and best utilization, we decided this can be utilized in the nearest unit from chloroalkali, which is the thermal treatment unit, to be utilized as a fuel in the furnace. So this will help us to reduce the overall sale gas which is required to fire up the furnace. So in order to implement this change and recover the hydrogen, mainly you need a cooler for condensate separation. You need a knockout drum to separate them physically, and a compressor to pressurize the hydrogen, and so it can be delivered to the furnace. So this is just a rough sketch to visualize what's the changes required. So from the outlet of the electrolyzer, instead of sending it to the stack, it will be diverted to the cooler, knockout drum separation, and then compressing to be sent to the burner. So by implementing this change, this will be equivalent to 19.5 saving of kilotons of CO2 per annum. And you can imagine, for this quantity, it's mainly equivalent to stopping permanently 4,300 cars a year. So this is just to imagine how much this 19.5 as a quantity. So this project currently it's in progress, and I hope that it will be commissioned soon. So that's it from my side. Thank you for your time, and thank you for giving me the opportunity. If you have any question, I will be happy to answer. And arigatou gozaimasu.
Thank you very much, Abdulaziz. Good luck with this new proposal on hydrogen of 19.5 thousand tons is an amazing target to look forward to. I mean, the energy efficiency measures also are really, and low carbon heat and heat extraction are very obviously. Any questions for Abdulaziz? Okay, so in that case, we'll just move to the next presentation, and this one is from Mr. Hamid Khalaf. Hamid is an energy and utilities process engineer, coordinating refinery site energy performance. SAMREF, he had experience in diesel hydrotreating, isomerization, and gas sweetening. Looking forward to listening to your presentation, Hamid. Thank you.
Assalamu alaikum. Good day, everybody. Thank you for the introduction. My name is Hamid Khalaf, process engineer from SAMREF, Saudi Aramco Mobile Refinery. Actually, it's one of Saudi Aramco JV with ExxonMobil, commissioned since 1984. My presentation today would be about energy initiatives that already completed and already resulted in CO2 reductions for last 5 years. SAMREF successfully implemented the 5 below projects and improvements idea in the refinery that resulted in energy saving as well as CO2 emission reductions are about 4% from refinery baselines emission. The first one was the crude waste heat boiler project. Second one is the C3 recovery from refinery of gas system. Third one is steam optimization. Fourth is the boiler feed water chemical treatment changed and upgraded to volatile component. The fifth one is the heater stack excess auto optimization. Looking to the crude waste heat boiler, initially a flue gas from a waste heat boiler was sent immediately to the stack. So this flue gas has a lot of energy can be conserved and switches to HB steam production. So that will help the boiler to reduce the boiler load, to have a spare capacity, and to maintain it N-1 as well. This, from energy point, will reduce the OPEX, since we will have lower fuel consumption in utility boilers. In addition, it will improve the EII energy. Resulted in lower CO2 emissions. So around 50 ton of HB steam will lower fuel gas saving around 3,300 MMBtu per day. We'll have two numbers VI credits. All overall emission reduction from CO2 would be around 65,000 ton per year. For a C3 recovery from a refinery of gas system, initially looking to the fuel gas system in the refinery, it contains of mainly two sources, sales gas and the off gas from the units. So whenever we recover off gas, so we will maximize the recovery for our propane and the plus component from a refinery of gas system. We'll have higher LPG to be sales. So this is would be the beneficial. So how we can implement it? Initially, we need to look to the cooling water temperature as we need to improve it as well to have main coolings. Looking to the main producer, for example, the UCB from the FCC block, where we need to maintain the primary absorber cleaning to have a C3 recovery. In addition, we implemented one of jump over from MDU to send the MDU of gas to the SGB unit for further recovery instead of directly using it in the fuel gas systems. So how we can get the CO2 lower emissions in this? So whenever energy demand will remain same in this block. However, when we replace a C3, we will need to have sales gas increase. So we are replacing a C3 with a C1. So we are getting a factor effects of a difference between a C3 and a C1. So replacing a C3 with a C1 will get you emissions reduction around 36,000 ton per year. For steam optimization, mainly looking to the FCC waste heat boiler economizer where it is installed, so around 10 ton of HB steam. However, as we know that the FCC flue gas temperature is limited by dew point since it has a lot of SOx and NOx. So to avoid any reliability corrosion issue, we should not exceed dew points since the concentration of the SOx is too high in that. For a steam leak fixation program, we have a clear and dedicated maintenance team specified for that job to identify all leaks to follow it to be fixation. That will save the water as well as the energy. For steam usage, for steam stripping, maintaining a ratio required for stripping steam, especially in crude and CHD units. So around, whenever we do all this, around 34,000 ton per year CO2 reduction we are getting. So still we have one challenge to be implemented and to be implemented as well, which is steam trap audits, which has potential numbers of 3,000 ton per year. So this would be the next challenge to SAMREF. Boiler feed water chemical treatment upgraded to volatile components. So in the boiler feed water, we replaced the conventional chemicals with the volatile amine-based chemicals. Actually, the idea here was purely reliability driven to improve the quality of the steam and the equipment and to reduce the corrosion over all steam network. However, luckily we are getting some beside benefits of that, where we have OPEX reduction from water saving, as we have lower blowdowns from all boilers and waste boilers. Also, we have from environmental points, we have lower wasted water from the blowdown and heat and energy recovery by reducing the CO2 emissions. Also, this is for operation guys, so they have easier handlings. They will treat with one chemical instead of 3 chemicals. Here, by saving the fuel due to less blowdown, around 260 MBTU fuel gas reduction per day. So CO2 reduction would be around 5,000 tons per year. The last one is the heater stack excess O2 optimization. As we know, whenever we have excess CO2, so the fuel gas would be excess and all the time. So whenever we reduce the O2 in the stack, we'll have fuel savings. So how we can do this? We can monitor the O2. We can upgrade the stack damper. So we upgraded the stack damper from actuator from pneumatic to electric. Also, we conduct lower O2 testing at the biggest heater in the refinery. So we are comparing the firebox or excess O2 versus the stack. So because the stack is not only, the stack is indication, you need to maintain the O2 actually in the firebox, not in the stacks. So by lowering this excess O2 around 21 MBTU ton per day of fuel savings. So we are lowering the emission by around 0.4 thousand ton per year. This is the end of my presentation. Thank you very much for listening. And if you have any questions, you are more than welcome.
Thank you, Hamid. Very interesting presentation. Any questions for Hamid? Okay, can do this. Yeah, okay. Okay.
And now, finally, we reach for the last step of this symposium. Again, I would like to thank you for your patience and sorry for the heavy agenda for yesterday. I would like to invite His Excellency Mr. Nakai for the closing remarks and Engineer Ahmed also for the closing remarks. On behalf of the General Secretariat of oapec, I would like to extend my sincere thanks to the attendants and the speakers who contributed to the success of this event, which we hope will be repeated in the coming years due to the excellent response and reactions we witnessed from everyone for discussing vital issues which are considered the cornerstone for or of the improving the performance of the petroleum industries in our countries. I also would like to extend my sincere thanks for the unlimited support from the Saudi Ministry of Energy, the generous hospitality, the tangible presence of the companies operating in the energy of the petroleum sector in the kingdom, the wonderful cooperation from the Japanese side, especially the Japanese Cooperation Center for Petroleum and Sustainable Energy, JCCP. Now with the closing remarks by oapec Secretariat and JCCP about the most important conclusion and recommendations of the symposiums, I have the honor to invite Engineer Ahmed for the remarks.
Thank you, Dr. Yasser. Ladies and gentlemen, I'd like to thank you for staying with us till now. And I would like also to thank the speakers for their very excellent presentations. They presented a very fruitful ideas, and most of them invited us to collaborate with each of us in order to bring our countries and industries for the excellent degree at the international level, and to minimize the challenges facing the refinery, especially regarding the emission reduction. I will give the stage to His Excellency Mr. Nakai to give the conclusion remark. Please.
Thank you very much, Maki-san, and also thank you very much, Yasser-san, your introduction. Of course, I have to appreciate Jamal-san and the oapec team, secretary team, to prepare this nice symposium. And also, after this meeting, I will meet His Excellency Prince Abdulaziz bin Salman. So I will say my thanks message to him directly. Because the Ministry of Energy's support is quite important for this symposium. We really also appreciate the participant speakers. And so I would like to thank you to the Japanese colleagues from Japan and JCCP colleagues also. Thank you very much. The title is The Pathways to Reduce Carbon Emission in Petroleum Downstream Field. That is a very good, appropriate title. There are many symposiums and seminars, but today we could focus on the issue in the downstream field of oil. And we could discuss a lot of different opinions. So it is a very appropriate title and at appropriate timing. And I recognized the priorities of the issues of each country, common issues among us, and the different issues among us. And also I recognize it is quite unique, quite interesting that also among yourself, oapec members, there are different of the priorities and issues. That makes me to understand more about OPEC and each of your member countries. I hope the Japanese input from speakers could help you better knowledge about to tackle your issues. We are now, in fact, very difficult and changing period in the world. We are facing energy transition. It's a very important issue. Of course, geopolitical change. But I hope we can together to challenge and overcome this difficult task. And we are surely, based on our cooperation, we can go ahead to overcome this kind of tasks and problems and find a better situation in the future. We should respect each other. We should respect each path of your energy transition. But based on this respect, we can find international cooperation to challenge those issues. So my last word is the human training or technical cooperation or knowledge dialogue, which we are doing, is so-called grassroots cooperation. But if you continue to have this grassroots cooperation for a long period, I'm sure we can create grand forest, grand oasis together. Thank you very much.
Thank you very much, Mr. Rakai. I have a list of recommendations took from the speakers and your discussions. Actually, there are a very long list of your valuable recommendations, but due to the limited time, I will review some of these recommendations, and we are open to receive your recommendation through the emails and any all of our communications, email or WhatsApp, or Dr. Yasser will give it to you. As we come to conclude this symposium, it is with great pleasure that I reflect on the valuable discussions and insights we have shared over the past 2 days. This symposium has been a remarkable platform for exchanging ideas, fostering collaboration, and generating innovative solutions. The recommendations and outcomes achieved during our time together have been both valuable and fruitful, paving the way for future advancement in our field. The speakers highlighted multiple pathways for reducing carbon emissions in downstream industries. Some solutions are readily available, while others are still in the early stages of development. These options include energy efficiency, using renewable energy, electrification, and applying carbon capture, utilization, and storage technologies. There are different options for improving the energy efficiency, including waste heat recovery, recovery of refinery off gases, as mentioned in this last sessions, steam optimization and fixing steam leaks, steam traps, upgrading heat exchangers and rotating equipment, improving insulation where relevant, optimizing process integration. Energy efficiency improvement are considered the preferred short-term pathways, but their improvements have some performance limitations. Therefore, long-term solutions will still be required, which come with additional investment costs, of course, such as carbon capture unit and sequestration, electrification, and using renewables and hydrogen with low carbon hydrogens. Production of low hydrogen, methane recovery are also on the agenda for medium to long-term carbon emission reduction. Fostering collaboration between academic sector and the petrochemical industry through the establishment of joint task force is essential. To accelerate collaboration, organizing regular meetings and conferences on this important topic will foster knowledge exchange and drive advancement in this field, the emission reduction. Addressing challenges in technology development and value chain creation is essential for reducing carbon emissions. The essential implementation of these technologies and the establishment of value chains rely on coordinated commercial, community, and government strategy. Governments play an essential role in formulating policies to stimulate investment. I will borrow the final statement from Mr. Muhammad Al-Shahrani, the last speaker. That the emission reduction and zero emission is not, it is a continuous process. So we have, it's need collaboration efforts to achieve our target for our environment and to meet the international legislation. Thank you very much, and I will let the stage to Dr. Yasser. Thank you for Mr. Nakai, and I would like to thank again GCCP for the fruitful cooperation, and we hope it will continue for a long time and for the benefit of all of us. Thank you.
Thank you, His Excellency, Mr. Nakai. Thank you, Engineer Ahmed, for your contribution. Finally, I think that we get the target from this symposium. Hope to see you soon in the next issue of our symposium soon, inshallah. I would like to ask you for a photo for all of the attendants. We can come here and try to get a photo session for us or a photo group. After that, we are invited for the lunch at the same restaurant as yesterday. Thank you very much for all of you, and see you soon, inshallah.
Joe فوق.
Please, the lunch at the same restaurant as yesterday, inshallah. You are welcome.